Welcome to Scientific Discovery Hub, the channel where we dive headfirst into the most mind-bending mysteries of the universe. Have you ever wondered if there's more to reality than what we can see, touch, or imagine? What if I told you that every choice you've ever made and every choice you didn't make plays out in its own universe? Today we're exploring one of the most thrilling ideas in modern science, the multiverse theory. Buckle up, because we're about to embark on a journey through parallel realities, quantum weirdness, and cosmic secrets that will challenge everything you think you know about existence. The multiverse theory suggests that our universe is just one of infinitely many, each with its own unique laws, dimensions, and versions of you. Imagine an infinite library where every possible story, yours, mine, and even stories we can't fathom, unfolds simultaneously. Sounds like science fiction? Actually, this idea is rooted in real science, from quantum mechanics to cosmic inflation and string theory. In this video, we'll break down how these mind-blowing concepts collide to paint a picture of a cosmos far stranger and grander than we ever imagined. We'll start by unpacking the wild world of quantum mechanics, where particles exist in multiple states until observed, leading to theories like the many worlds interpretation, where every decision splits reality into branching universes. Then we'll zoom out to the largest scales, exploring how cosmic inflation could create a foam of bubble universes, each with its own Big Bang. Along the way, we'll tackle string theory's hidden dimensions, the mysterious role of dark matter, and even the possibility that black holes are portals to other realities. And yes, we'll ask, could our universe be a simulation? But the multiverse isn't just about science, it's about us. How does the idea of infinite realities affect our understanding of free will, identity, and humanity's place in the cosmos? We'll touch on the Anthropic principle, the Fermi paradox, and the haunting question, are we alone, or just one thread in an infinite tapestry of life? Whether you're a curious beginner or a sci-fi enthusiast, this video will take you on a roller coaster through the frontiers of physics, philosophy, and imagination. Hit play to dive deeper. And don't forget to like, subscribe, and hit that notification bell so you never miss a mind-expanding adventure. Together, let's unlock the universe one theory at a time. In the vast expanse of human imagination, few concepts evoke as much awe and bewilderment as the multiverse. Picture a cathedral of infinite proportions, its vaulted ceilings studded with stars, its arches carved not from stone but from the very fabric of time and space. Within this cathedral lies an endless library, its shelves stretching beyond sight, each volume bound in the ink of possibility itself. Every book contains a story, one you might have lived, one you could never have imagined, or one that defies the logic of your own reality. Some tomes recount the tale of a universe where gravity is a gentle whisper rather than a relentless pull, where light bends in ways we cannot perceive. Others chronicle lives where pivotal choices diverged. A scientist who abandoned their research, a musician who never composed a symphony, a child who was never born. This is the multiverse, not a mere collection of universes, but a tapestry woven from every permutation of existence. Every answer to the question, what if? The multiverse is not a product of fantasy. It is a hypothesis rooted in the most rigorous branches of modern science. Theoretical physicists, cosmologists, and mathematicians have spent decades grappling with the implications of a cosmos that may extend far beyond what we observe. From the subatomic realm of quantum mechanics to the explosive birth of the universe in the Big Bang, the seeds of the multiverse are sown in the very laws that govern our reality. Yet, for all its mathematical elegance, the multiverse remains an enigma, a proposition that challenges our understanding of identity, purpose, and the nature of existence itself. To entertain the possibility that countless other universes exist alongside ours is to confront a truth both humbling and exhilarating. Our reality is but a single thread in an infinite loom, and every moment of our lives is mirrored in 1,000 alternate forms across the cosmic expanse. This notion, though daunting in its scope, invites us to consider the profound interconnectedness of all things. If every decision, every chance encounter, every unspoken word splits the universe into new branches, then the multiverse becomes a mirror reflecting the infinite complexity of existence. It is a reminder that the universe is not a static stage, but a dynamic, ever-evolving narrative shaped by forces both seen and unseen. As we embark on this exploration, we will journey through the corridors of theoretical physics, the echoes of cosmic inflation, and the labyrinthine dimensions proposed by string theory. We will ask not only whether the multiverse exists, but what it means for our place within it. And in doing so, we may glimpse the contours of a reality far greater than ourselves. A reality where the boundaries between the possible and the impossible dissolve into the infinite. The multiverse is not a singular idea, but a mosaic of hypotheses, each emerging from different corners of theoretical physics. At its heart lies the recognition that the universe we inhabit is governed by laws that permit a staggering array of solutions. Take, for instance, the equations of general relativity, which describe the curvature of space-time. These equations do not confine themselves to a single solution for the structure of the cosmos. Instead, they allow for an almost limitless variety of configurations. Some of these solutions suggest universes with different numbers of spatial dimensions, others with altered fundamental constants, and still others where the very nature of matter and energy differs from what we know. This mathematical openness is the first clue that our universe might not be unique, but one of many, each a distinct chapter in the grand story of existence. One of the most compelling frameworks for the multiverse comes from the theory of cosmic inflation, proposed in the 1980s by physicists such as Alan Guth and Andre Linde. Inflation describes a period of exponential expansion that occurred fractions of a second after the Big Bang. During this fleeting era, the universe ballooned from a subatomic speck to a vast expanse, smoothing out irregularities and setting the stage for the formation of galaxies. However, inflation is not a one-time event. According to Linde's eternal inflation model, the process of expansion continues indefinitely in most regions of space, giving rise to a fractal-like structure of pocket universes. Each pocket universe undergoes its own Big Bang, its own evolution, and its own set of physical laws. In this picture, our universe is but one bubble in an endless sea of bubbles, each separated by regions of rapidly inflating space. The implications are staggering. If eternal inflation is correct, then the number of universes is infinite, and each one is isolated from the others by distances so vast that no signal, not even light, could traverse them. Quantum mechanics provides another avenue to the multiverse, particularly through the many worlds interpretation, Nash and MWI, developed by Hugh Everett III in the 1950s. At the heart of quantum theory is the principle of superposition, wherein particles exist in multiple states simultaneously until measured. The MWI takes this idea further, positing that every possible outcome of a quantum event actually occurs, each in its own branch of reality. Imagine flipping a coin. In one universe, it lands heads, in another, tails. When you observe the result, you become entangled with one of these outcomes, experiencing only one branch while all others continue to exist independently. Over time, these branching realities multiply exponentially, creating a tree-like structure of parallel universes. Unlike the bubble universes of inflation, the quantum multiverse is intimately connected to our own, with each split occurring at the smallest scales. Yet, because these branches are decoherent, meaning they no longer interfere with one another, we experience only one path of history, unaware of the countless others unfolding in tandem. String theory, the ambitious attempt to unify quantum mechanics and general relativity, offers yet another perspective on the multiverse. At its core, string theory replaces point-like particles with vibrating strings, whose different modes of vibration correspond to different particles. However, the mathematics of string theory demands extra spatial dimensions, typically 10 or 11, far beyond the 3 we experience. These additional dimensions are compactified, curled up at scales too small to detect. The way these dimensions are compactified determines the properties of the resulting universe, such as the strength of fundamental forces and the types of particles that exist. Crucially, there are an astronomical number of ways to compactify the extra dimensions, each giving rise to a distinct vacuum state or configuration of the universe. This leads to the landscape of string theory, a hypothetical set of approximately $10–50 possible universes, each with its own unique physical laws. In this framework, the multiverse is not just a byproduct of cosmic inflation or quantum mechanics, but a natural consequence of the mathematical structure of string theory itself. Together, these theories paint a picture of a cosmos far richer and more complex than previously imagined. Cosmic inflation suggests an infinite ensemble of universes, each born from its own inflationary event. Quantum mechanics implies a branching multiverse where every possibility becomes actuality. String theory hints at a landscape of universes, each defined by the geometry of hidden dimensions. While these ideas differ in their details, they share a common theme. The universe is not a singular entity, but a vast interconnected web of realities. This realization challenges our conventional notions of uniqueness and permanence, replacing them with a vision of existence as fluid, multifaceted, and endlessly diverse. The multiverse is not merely a scientific hypothesis, it is a philosophical earthquake, shaking the foundations of our understanding of self, causality, and meaning. If every possible outcome exists in some universe, then the very concept of uniqueness dissolves into abstraction. Consider the infinite variations of yourself that might exist across the multiverse. One who became a poet instead of a physicist, one who never encountered love, one who survived a tragic accident that claimed your life in this reality. Each of these versions shares your genetic code and formative experiences up to a certain point, yet diverges at moments of choice or chance. This raises a haunting question: what does it mean to be you when your essence is replicated across infinite realities? Does identity persist in such a context, or is it reduced to a statistical pattern, a fleeting echo in an ocean of possibilities? The implications for free will are equally profound. If every decision spawns a new branch of reality, then the illusion of agency is exposed as a necessary fiction. In one universe, you choose to pursue a career in medicine. In another, you abandon your studies to travel the world. Both outcomes occur, yet you experience only one. This suggests that free will, as we understand it, is not about selecting a singular path, but participating in the unfolding of a predetermined tapestry. The weight of responsibility feels diminished, for no action is truly final. Every consequence is offset by an infinite array of alternatives. Yet this also fosters a strange liberation. If suffering and failure exist in parallel universes, then perhaps they are not absolute truths, but transient states, reminders that existence is not confined to a single trajectory. The multiverse reframes our struggles as threads in a broader narrative, urging us to embrace the fluidity of identity and the impermanence of circumstance. Beyond individual identity, the multiverse challenges the notion of a singular cosmic order. For centuries, humanity has sought meaning in the constancy of the universe, its predictable laws, its elegant symmetries, its apparent fine-tuning for life. The multiverse, however, suggests that these laws are not universal but contingent. In some universes, gravity might be weaker, rendering stars unstable and life improbable. In others, the speed of light could be faster, compressing time into a blur. The conditions that allow for our existence are not unique but rare, a statistical fluke in an infinite lottery. This realization is both humbling and disorienting. It strips away the comforting idea of a purposeful design, replacing it with a cosmic indifference that is both vast and intimate. If our universe is one of many, then its beauty and mystery are not exceptional but inevitable, a product of the multiverse's inexhaustible creativity. Yet, the multiverse is not without its paradoxes. One of the most perplexing is the issue of communication. If other universes exist, why have we not detected them? The answer lies in the nature of the barriers separating them. In the case of eternal inflation, the distances between bubble universes are so immense that even light cannot bridge the gap. In the quantum multiverse, decoherence ensures that branches remain isolated, their histories irreconcilable. String theory's landscape of vacua presents a similar challenge. The differences in physical laws render interactions between universes impossible. These insurmountable divides create a profound loneliness. We are surrounded by infinite realities, yet we are eternally alone within them. This isolation is not merely physical but existential. The knowledge that countless versions of ourselves exist in parallel universes does not bring comfort. It deepens the ache of separation, a yearning to reach across the void and touch the lives we could have led. The multiverse also compels us to reconsider the nature of probability and the limits of knowledge. In an infinite ensemble of universes, even the most improbable events must occur somewhere. A universe where every lottery winner is chosen by chance is statistically guaranteed to exist alongside one where the same person wins every draw. This raises unsettling questions about the reliability of our observations. How can we distinguish between what is likely and what is merely a fluke in the multiverse's grand design? The concept of probability loses its meaning when all possibilities are realized. This challenges the scientific method, which relies on reproducibility and statistical significance. If every experimental outcome exists in some universe, then no result can be considered definitive. It is always possible that we inhabit the branch where an anomaly occurred. The multiverse thus introduces a radical uncertainty, a reminder that our understanding of reality is forever incomplete. Despite these challenges, the multiverse offers a balm to the existential despair that often accompanies the realization of our cosmic insignificance. By expanding the boundaries of existence, it transforms the void into a source of wonder rather than dread. In the face of an infinite multiverse, the petty concerns of daily life fade into perspective. The wars we wage, the grudges we hold, the fears that haunt us, all are ephemeral against the backdrop of eternal multiplicity. The multiverse invites us to embrace a humility that is not defeatist but liberating. It teaches that our individual stories, while deeply meaningful to us, are but fragments of a larger whole. In this vast and varied cosmos, every act of kindness, every spark of creativity, and every moment of connection resonates across the infinite, leaving an indelible mark on the tapestry of existence. To grasp the full scope of the multiverse, we must first descend into the quantum realm, the subatomic world where particles dance on the edge of existence, where the rules of classical physics dissolve into the probabilistic haze of wave functions. Here, in this domain of uncertainty, the seeds of the multiverse are sown. Quantum mechanics reveals a universe far stranger than Newtonian intuition permits, one where particles can occupy multiple positions at once, where observation collapses the wave of possibilities into a single outcome. Yet, for all its peculiarities, quantum mechanics remains the most precise and successful theory in physics. Its predictions confirmed time and again by experiment. But what if the act of observation is not the end of the story, but the beginning of a branching narrative? What if every quantum event, every flicker of energy births new universes in an endless cascade of possibilities? This is the crux of the many worlds interpretation, a hypothesis that reimagines the quantum landscape as a vast, interconnected web of realities. Unlike the Copenhagen interpretation, which posits that observation collapses the wave function into a single state, the many worlds interpretation asserts that all outcomes coexist, each manifesting in its own branch of the multiverse. The famous double-slit experiment, where particles exhibit wave-like interference patterns until measured, becomes a testament to this branching. When an electron passes through the slits, it does not simply choose one path or the other. It traverses all paths simultaneously, with each trajectory existing in a separate universe. The interference pattern we observe is not an artifact of randomness, but the shadow of an infinite multitude of realities overlapping. As we peer deeper into the quantum abyss, we find that the multiverse is not a distant abstraction, but a fundamental feature of reality itself. The next segment will explore the quantum fabric of existence, unraveling the mysteries of superposition, entanglement, and the role of the observer in shaping reality. We will see how the quantum multiverse intertwines with the cosmic inflationary model, offering a unified vision of a universe that is both infinitely small and infinitely large. In this journey, we will confront the paradoxes that arise when the microcosm meets the macrocosm, seeking answers to questions that have haunted physicists and philosophers alike. Is the multiverse a necessary conclusion of quantum mechanics, or is it an overreach of speculative thought? Can we ever hope to verify its existence, or are we forever confined to the shadows of our own universe? The answers may lie in the delicate interplay of theory and observation. in the whispers of quantum fluctuations imprinted on the cosmic microwave background. They may emerge from the search for a unified theory of everything, a framework that bridges the quantum and the cosmic. Whatever the case, one thing is certain. The multiverse is not merely a hypothesis about the structure of the cosmos. It is a revolution in thought, a paradigm shift that compels us to rethink the very nature of reality. As we step into the quantum labyrinth, we carry with us the questions that have driven humanity since the dawn of consciousness. What is our place in the universe? Are we alone? Or are we part of a vaster, unknowable whole? The answers may lie not in the stars above, but in the infinitesimal dance of particles beneath our feet. Beneath the familiar rhythms of the macroscopic world, where objects have defined positions, time flows linearly, and cause and effect reign supreme, lies a hidden theater of chaos and possibility. At the heart of this enigmatic domain, the quantum realm, particles defy intuition, existing as both entities and abstractions, their states suspended in a haze of probability. Here the rules of classical physics dissolve, replaced by a language of mathematics that speaks in probabilities rather than certainties. In this subatomic landscape, the very notion of reality becomes fluid, shaped by observation and teeming with potential. It is a realm where a single photon can traverse multiple paths simultaneously, where electrons orbit nuclei like clouds of charge, and where the act of measuring something fundamentally alters what is being measured. This is the quantum world, a cosmos within our cosmos, where the boundaries between existence and non-existence blur, and where the familiar laws of cause and effect give way to the strange logic of quantum mechanics. At the center of this quantum enigma lies the paradox of superposition, a principle that allows particles to inhabit multiple states at once until they are observed. Consider the famous thought experiment of Schrödinger's cat, a feline trapped in a box with a vial of poison, whose fate is tied to the random decay of a radioactive atom. Until someone opens the box to observe the outcome, the cat exists in a peculiar limbo, simultaneously alive and dead. This unsettling scenario illustrates the core tenet of quantum mechanics, that the universe, at its most fundamental level, is not a fixed tapestry of events, but an ever-shifting mosaic of probabilities. The implications are profound. If reality is not determined until it is observed, then what defines an observer? Does the mere act of looking shape the fabric of existence itself? These questions, though centuries old, remain unresolved, echoing through the corridors of modern physics and philosophy alike. Yet the quantum realm is not merely a stage for paradoxes. It is also a source of boundless wonder. The dance of probabilities that governs this microscopic world mirrors the grand cosmic order above, where stars are born from the collapse of interstellar clouds and galaxies spiral in gravitational harmony. Just as quantum fluctuations may have seeded the structure of the universe in its infancy, the same principles of uncertainty and potentiality ripple outward, influencing the fate of atoms, planets, and perhaps even the cosmos itself. In this sense, the quantum realm is not an isolated curiosity, but an integral thread in the universal fabric, a reminder that the laws governing the smallest particles are deeply intertwined with those shaping the largest structures in existence. To comprehend this connection is to glimpse the unity of the universe, a unity that transcends scales and challenges the limits of human perception. As we venture deeper into the quantum realm, we encounter a reality that defies the deterministic worldview once championed by Newtonian physics. Instead of a clockwork universe where every motion is predictable, we find a cosmos that thrives on uncertainty, where the future is not etched in stone but written in the probabilities of quantum waves. This shift in perspective is not merely academic. It reshapes our understanding of existence itself. If the universe is a tapestry of potentialities, then every moment is a choice among infinite possibilities, every decision a branch in the tree of reality. In this light, the quantum realm is not just a domain of particles and equations. It is a mirror reflecting the fundamental nature of existence, a reminder that the cosmos is not a static entity, but a dynamic, evolving story of probabilities waiting to unfold. At the heart of quantum mechanics lies the wave function, a mathematical construct that encapsulates the probabilistic nature of particles. unlike classical physics, which describes objects with precise coordinates and velocities. Quantum mechanics uses the wave function to represent the likelihood of finding a particle in a particular state. This equation, often denoted by the Greek letter psi maish, evolves over time according to the Schrödinger equation, a fundamental law that governs the dynamics of quantum systems. The wave function itself is not a tangible entity, but a tool for predicting probabilities, an abstract representation of the myriad possibilities inherent in a quantum system. For example, the wave function of an electron in an atom does not pinpoint its exact location, but instead provides a cloud of probabilities, indicating regions where the electron is more likely to be found. This probabilistic description is not a limitation of our knowledge, but a fundamental feature of reality at the quantum scale. One of the most striking demonstrations of this quantum behavior is the double-slit experiment, a cornerstone of quantum theory that reveals the dual nature of particles. When particles such as photons or electrons are fired at a barrier with two slits, they create an interference pattern on a detection screen, akin to ripples in a pond overlapping, to form complex waves. This pattern arises because the particles behave as waves, passing through both slits simultaneously and interfering with themselves. However, when the experiment is modified to observe which slit a particle passes through, the interference pattern vanishes, and the particles instead produce two distinct clusters corresponding to the individual slits. This phenomenon, known as wave-particle duality, underscores the paradoxical nature of quantum entities. They exhibit properties of both particles and waves, depending on how they are observed. The act of measurement in this case forces the wave function to collapse into a definite state, transforming the probabilistic spread into a specific outcome. The collapse of the wave function is central to the Copenhagen interpretation, one of the most widely accepted frameworks for interpreting quantum mechanics. According to this view, the act of observation is not a passive process, but an active intervention that irrevocably alters the system being measured. Before observation, a quantum system exists in a superposition of all possible states, each represented by a component of the wave function. Upon measurement, however, the wave function collapses into a single eigenstate, corresponding to the observed outcome. This collapse is instantaneous and irreversible, leaving behind a definite result that aligns with the probabilities encoded in the wave function. The Copenhagen interpretation thus introduces a profound asymmetry between the quantum world and the classical realm. While particles exist in a haze of probabilities, the macroscopic world we inhabit is governed by certainty and determinism. The implications of this collapse extend beyond the laboratory, challenging our understanding of causality and the nature of reality. If the act of observation determines the outcome of a quantum event, then the observer plays an essential role in shaping reality itself. This raises the tantalizing question: what constitutes an observer? Is it a conscious entity, or can any interaction with the environment suffice? The ambiguity surrounding this issue has sparked decades of debate among physicists and philosophers, with some arguing that the collapse occurs only when information is recorded, while others propose alternative interpretations that eliminate the need for an observer altogether. Regardless of the resolution, the collapse of the wave function remains a defining feature of quantum mechanics, a mechanism that transforms the abstract probabilities of the quantum realm into the tangible outcomes we perceive in the macroscopic world. Beyond the collapse, the wave function also gives rise to another counterintuitive phenomenon: quantum entanglement. When two particles become entangled, their states become correlated in such a way that the measurement of one instantaneously affects the state of the other, regardless of the distance separating them. This spooky action at a distance, as Einstein famously described it, defies classical intuitions about locality and causality. Entangled particles appear to share an inseparable connection, as if their properties are not independent, but linked across space and time. This phenomenon has been confirmed through numerous experiments, including Bell tests that rule out local hidden variable theories and demonstrate the non-local correlations predicted by quantum mechanics. Entanglement further reinforces the idea that quantum systems are not isolated entities, but interconnected networks of probabilities, their fates intertwined in ways that transcend classical understanding. The mathematical elegance of the wave function and the empirical validation of quantum phenomena underscore the robustness of quantum mechanics as a theoretical framework. Despite its seemingly paradoxical nature, the theory has made countless successful predictions, from the energy levels of atoms to the behavior of semiconductors in modern electronics. The wave function, though abstract, serves as a bridge between the probabilistic quantum world and the deterministic classical realm, allowing scientists to model and predict the outcomes of experiments with remarkable precision. Yet, for all its success, quantum mechanics remains incomplete, its foundation still shrouded in mystery. The collapse of the wave function, the role of the observer, and the nature of entanglement continue to elude a unified explanation, hinting at deeper truths that lie beyond our current understanding. If the act of observation collapses the wave function and shapes reality, then the question of who or what qualifies as an observer becomes paramount. In the Copenhagen interpretation, the observer is typically associated with a measuring device, such as a detector or a camera, which records the outcome of a quantum event. However, this definition raises a host of philosophical quandaries. Does the observer need to be conscious? Can a machine or an animal serve as an observer? Or is the role reserved exclusively for sentient beings? These questions blur the line between science and philosophy, challenging the conventional boundaries of objectivity in physics. Some interpretations suggest that the observer is not an external agent, but an intrinsic part of the quantum system itself, with the act of measurement emerging from the interaction between the system and its environment. This perspective, known as decoherence, shifts the focus from conscious observers to the entanglement of quantum systems with their surroundings, where environmental interactions effectively measure the system and suppress superpositions. While decoherence offers a compelling explanation for the emergence of classical behavior, it does not fully resolve the conundrum of the observer's role, leaving open the possibility that consciousness itself may play a unique part in the collapse of the wave function. The implications of this ambiguity extend beyond the laboratory and into the broader philosophical discourse on the nature of reality. If observation shapes reality, then the universe may be inherently participatory, with observers not merely perceiving the world, but actively co-creating it. This notion resonates with certain interpretations of quantum mechanics, such as the von Neumann-Wigner interpretation, which posits that consciousness is the ultimate observer that collapses the wave function. Proponents of this view argue that the universe exists in a state of pure potential until it is perceived by a conscious mind, suggesting that the cosmos is in some sense a mental construct. While this interpretation remains controversial and lacks empirical support, it raises fascinating questions about the relationship between consciousness and the physical world. Could the human mind be uniquely attuned to the quantum realm, capable of collapsing wave functions in ways that inanimate matter cannot? Or is consciousness itself an emergent property of quantum processes occurring in the brain, with the observer effect being a natural consequence of biological complexity? These questions, though speculative, highlight the profound interplay between physics and philosophy, urging us to reconsider the boundaries of science and the limits of human understanding. Another interpretation that grapples with the observer effect is the many worlds interpretation, MWI, proposed by Hugh Everett III in 1957. Unlike the Copenhagen interpretation, which posits a collapse of the wave function upon observation, MWI eliminates the need for an observer altogether by suggesting that all possible outcomes of a quantum event actually occur, each branching into a separate parallel universe. In this framework, the universe is not a single linear progression of events, but an ever-expanding tree of realities, where every quantum decision spawns a new branch. For instance, in the case of Schrödinger's cat, the cat is both alive and dead in two distinct universes, each containing a version of the observer who perceives one of the outcomes. From the perspective of an individual within a particular universe, the wave function appears to collapse because they are confined to experiencing only one branch of reality. However, from a broader multiversal standpoint, all possibilities coexist, and the illusion of a singular outcome arises from the observer's limited perspective. The many worlds interpretation offers a radical reimagining of reality, one in which the universe is not a static entity, but a dynamic fractal structure of infinite possibilities. Each quantum event, whether the spin of an electron, the decay of a nucleus, or the movement of a subatomic particle generates a new branch, multiplying the number of universes exponentially. This proliferation of realities challenges our conventional understanding of existence, suggesting that the cosmos is far vaster and more intricate than previously conceived. In this view, every decision, every choice, and every random fluctuation gives rise to a new universe, creating an infinite ensemble of parallel worlds where all possible histories and futures unfold simultaneously. The implications for free will and determinism are particularly striking. If every possible action is realized in some universe, then the concept of choice becomes a matter of perspective, with each decision leading to a branching path rather than a single predetermined outcome. Despite its conceptual elegance, the many worlds interpretation is not without its critics. One of the primary objections is the lack of empirical evidence supporting the existence of parallel universes. While the theory makes mathematically consistent predictions that align with quantum mechanics, it is difficult to test experimentally because the other branches of reality are, by definition, inaccessible to observers within their own universe. This raises questions about the scientific validity of MWI, as it relies on assumptions that cannot be directly verified. Additionally, the interpretation's reliance on an infinite number of universes introduces conceptual challenges, such as the problem of defining probabilities in a multiverse, where all outcomes are equally real. How can we assign meaning to the probabilities encoded in the wave function if every possibility is actualized somewhere? Critics argue that MWI sacrifices simplicity for explanatory power, offering a solution to the measurement problem at the cost of introducing an uncountable infinity of universes. Beyond the many worlds interpretation, other approaches attempt to reconcile the observer effect with the quest for a unified theory of physics. One such approach is the de Broglie-Bohm theory, also known as pilot wave theory, which proposes that particles have definite positions at all times, guided by a pilot wave that determines their trajectories. In this interpretation, the wave function does not collapse, but instead continues to evolve according to the Schrödinger equation, while the particles follow deterministic paths influenced by the wave. The apparent randomness in quantum measurements arises from the observer's ignorance of the initial conditions of the particles, rather than an inherent indeterminacy in the system itself. While this theory successfully reproduces the predictions of quantum mechanics, it reintroduces the concept of hidden variables, parameters not accounted for in standard quantum theory, which many physicists find unsatisfactory. Nonetheless, pilot wave theory demonstrates that the observer effect does not necessarily imply a fundamental indeterminacy in the universe, offering an alternative perspective on the nature of quantum reality. The exploration of the observer effect also intersects with the broader challenge of unifying quantum mechanics with general relativity, the theory that describes the force of gravity and the structure of space-time. In the realm of quantum gravity, researchers seek to reconcile the probabilistic nature of quantum mechanics with the deterministic curvature of space-time in general relativity. One of the most promising avenues in this pursuit is string theory, which posits that fundamental particles are not point-like, but rather vibrating strings in higher dimensional space. String theory introduces the possibility of extra dimensions beyond the familiar 3 spatial dimensions and 1 temporal dimension, suggesting that the universe may have a more complex geometric structure than previously imagined. In this framework, the observer effect may take on new dimensions, literally and figuratively, as the interplay between quantum fluctuations and the geometry of space-time could influence the emergence of classical reality. The philosophical ramifications of the observer effect extend to our understanding of time itself. In a universe governed by quantum probabilities, time may not be a linear progression, but a multi-dimensional construct, with each quantum event contributing to the branching of timelines. This perspective aligns with the block universe theory, which views past, present, and future as equally real, existing in a 4-dimensional space-time continuum. In this model, the passage of time is an illusion, and the universe is a static, unchanging whole. The observer effect, in this context, becomes a mechanism for selecting a particular slice of the block universe, with each observation carving out a specific path through the continuum. This raises the intriguing possibility that time is not an objective feature of the universe, but a subjective experience shaped by the observer's interaction with quantum systems. Ultimately, the observer effect and its implications for the nature of reality remain one of the most profound mysteries in modern physics. Whether through the lens of the Copenhagen interpretation, the many worlds interpretation, or alternative frameworks, the quantum realm, with its tapestry of probabilities and uncertainties, invites us to reconsider the very fabric of existence, challenging us to embrace a universe that is not only vast and complex, but also deeply interconnected. As we peer into the depths of quantum mechanics, we find not just a set of mathematical rules governing particles, but a reflection of the cosmos itself, a reminder that the act of observing is not merely a passive process, but an active participation in the unfolding story of the universe. As we step back from the quantum realm, where particles dance in a haze of probabilities, we are compelled to ask, how do these ephemeral fluctuations and probabilistic behaviors scale to the vast deterministic cosmos we perceive? The answer may lie in the realm of string theory, a bold theoretical framework that seeks to unify the forces of nature by positing that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings, hypothesized to exist in a multi-dimensional space, offer a tantalizing bridge between the quantum world and the grand architecture of the cosmos. In this framework, the same principles of probability and uncertainty that govern the subatomic realm may manifest on a cosmic scale, where the vibrations of strings in extra dimensions give rise to the forces and particles we observe. String theory introduces the concept of extraspatial dimensions beyond the familiar three, proposing that the universe may have as many as 10 or 11 dimensions, compactified into minuscule curled geometries imperceptible to our senses. These hidden dimensions, though invisible, could hold the key to explaining the fundamental forces of nature, including gravity, which has long resisted integration into the quantum framework. By embedding quantum mechanics within a higher dimensional geometry, string theory suggests that the probabilistic nature of quantum events may emerge from the interactions of strings in this expanded space. Just as quantum fluctuations at the Planck scale seed the structure of the early universe, the vibrations of strings in higher dimensions could give rise to the cosmic web of galaxies and the large-scale structure we observe today. This transition from the quantum to the cosmic is not merely a matter of scale, but of perspective. The same principles that allow particles to exist in superpositions and entangle across distances may underpin the interconnectedness of the universe at all levels. As we prepare to explore string theory in greater depth, we must recognize that the cosmos, much like the quantum realm, is a tapestry of potentialities, where the interplay between probability and geometry shapes the destiny of all things. In this light, the journey from the infinitesimal to the infinite is not a departure, but a continuation, a seamless unfolding of the universe's deepest mysteries, waiting to be revealed. Beneath the shimmering veil of stars and galaxies lies a universe far more intricate than the three-dimensional expanse we inhabit. Our senses, evolved to navigate Earth's surface, perceive only length, width, and height. Yet, if the whispers of string theory are true, reality is a symphony of hidden dimensions, folded so tightly into the fabric of space that they elude detection. Imagine a world where every particle you encounter, the electrons orbiting atoms, the photons streaming from distant stars, is not a discrete dot of matter, but a minuscule vibrating string. These strings, no thicker than a Planck length, a scale so infinitesimal it defies comprehension, resonate in harmonies that define the properties of all known forces and matter. Their vibrations are the universe's fundamental notes, a cosmic melody whose frequencies dictate whether a string becomes an electron, a quark, or a graviton. But for this music to play without discord, the mathematics demands something extraordinary. Extraspatial dimensions curled into geometries so alien they challenge the imagination. This notion that our universe may possess 10, 11, or even 26 dimensions arises not from whimsy but from the relentless pursuit of unification. For centuries, physicists have sought to reconcile two pillars of modern science: quantum mechanics, which governs the subatomic realm, and general relativity, which describes the curvature of spacetime on cosmic scales. These frameworks, though wildly successful in their domains, clash when probed at the smallest scales. String theory offers a bridge, replacing point-like particles with vibrating strings, whose interactions resolve the contradictions. Yet this elegant solution comes at a cost. The equations demand more dimensions than we can see. These dimensions, if they exist, are not merely theoretical abstractions. They are the scaffolding upon which the cosmos is built, a geometry so profound that it redefines our place in the universe. To grasp the magnitude of this revelation, consider the scale of the hidden. If the extra dimensions are compactified, as proposed by Calabi-Yau manifolds, they might resemble a microscopic rose petal curled within a single atom, just as a garden hose appears one-dimensional from afar but reveals a circular cross-section up close. These dimensions hide in plain sight, their complexity masked by their size. To imagine them is to peer into the heart of reality itself, where the laws of physics are not arbitrary, but emerge from the topology of space. Here in this unseen architecture lies the key to understanding not only the nature of matter, but the very essence of existence. At the core of string theory lies a deceptively simple idea. Replace the point-like particles of quantum field theory with one-dimensional objects called strings. These strings, which vibrate at specific frequencies, give rise to the diverse particles observed in nature. A string oscillating in one mode becomes an electron, another, a photon, a third, a gluon binding atomic nuclei. The diversity of the universe, from the flicker of light to the hum of dark matter, emerges from the same fundamental ingredient, a string's resonant frequency. This unifying principle resolves a long-standing problem in physics: the inability to merge quantum mechanics with general relativity. In the subatomic realm, where particles interact via probabilistic rules, strings provide a framework that avoids the infinities that plague quantum gravity. Their extended structure smears out singularities, allowing gravity to behave peacefully alongside other forces. Yet, this elegance hinges on a startling requirement. The mathematics of string theory only works in a universe with 10, or in some formulations 26, dimensions. Why 10? Because the equations governing string vibrations demand a specific number of spatial directions to remain consistent. In our everyday experience, we move freely in 3 dimensions up-down, left-right, forward-backward, but string theory posits 6 additional dimensions, compactified into shapes so small they escape direct observation. These dimensions are not infinite, but curled into intricate geometries known as Calabi-Yau manifolds. First envisioned by mathematicians in the 1950s, these manifolds are complex, multi-holed structures that resemble the surfaces of abstract art. Their topology determines the possible vibrational modes of strings, effectively shaping the physical laws of our universe. The mathematics of Calabi-Yau manifolds is both beautiful and maddeningly precise. A single manifold can host thousands of distinct configurations, each corresponding to a unique set of physical constants. This multiplicity hints at a deeper truth. String theory does not predict a single universe, but a vast landscape of possibilities. Each Calabi-Yau shape is a blueprint for a different cosmos, with its own arrangement of forces and particles. Some universes might harbor life as we know it. Others might be barren voids governed by alien physics. This realization transforms string theory from a mere model of particle interactions into a cosmic inventory of potential realities. The implications of this geometry extend beyond the abstract. If the extra dimensions are real, they could explain anomalies in our observations. For instance, the weakness of gravity compared to other forces might arise because gravitational strings, gravitons, can vibrate in the hidden dimensions, diluting their strength in our 3-dimensional world. Similarly, the hierarchy problem, the stark difference between the energy scales of gravity and quantum mechanics, might find resolution in the geometry of the compactified space. In this view, the universe is not a static stage, but a dynamic sculpture, its form dictated by the interplay of strings and dimensions. The most radical implication of string theory is not merely the existence of extra dimensions, but the possibility that our universe is but one leaf on a cosmic tree. According to the brain-world hypothesis, our universe exists as a 3-dimensional membrane, what physicists call a three-brain, floating in a higher dimensional bulk. Other brains, potentially infinite in number, may drift alongside ours, separated by distances imperceptible to us. In this framework, the particles and forces we observe are confined to our brain, unable to traverse the bulk. Gravity, however, might escape its bounds, its reach extending across the hidden dimensions. This idea offers a tantalizing explanation for gravity's feebleness. Its influence is diluted, stretched thin by the vastness of the extra space, but the consequences go further. If brains can collide or vibrate, their interactions might give rise to cataclysmic events. Some models suggest that the Big Bang itself was triggered by the collision of two brains, a cosmic crash that unleashed the energy seeding our universe. Such a perspective reframes the origin story of the cosmos, transforming it from a singular event into a recurring phenomenon in a multiversal ocean. Each collision births a new universe, each with its own brain-bound laws and dimensions. Our universe, in this view, is not unique but one among countless others, each a bubble in a multidimensional foam. This vision of a multiverse challenges our perception of reality. It suggests that the constants of nature, the mass of the electron, the strength of the nuclear force, are not universal truths, but accidents of our brain's geometry. In other universes, these values might differ drastically, rendering them inhospitable to life as we know it. This idea, known as the Anthropic principle, posits that we observe a universe compatible with our existence simply because we cannot exist otherwise. It is a humbling reminder that our reality is but a sliver of a far grander whole. Moreover, the brain world concept opens doors to speculative phenomena. Could there be parallel universes where time flows backward, where the electromagnetic force dominates over gravity, or where consciousness arises in forms alien to our biology? While these questions remain unanswered, they underscore the transformative power of string theory. By revealing the possibility of a multiverse, it forces us to confront the limits of our knowledge and the vastness of what lies beyond. Even more astonishing is the suggestion that our universe is not merely a brain, but a fleeting configuration in an ever-shifting landscape. In the context of M-theory, a proposed extension of string theory that unifies its 5 variants, the bulk is not empty but filled with a dynamic interplay of brains, strings, and membranes. These entities might merge, split, or decay, their transformations echoing through the higher dimensional expanse. In this view, the cosmos is not a static construct, but a living entity, evolving through cycles of creation and destruction. If string theory paints a picture of a multiverse teeming with brains and hidden dimensions, it also raises a fundamental question: how did this vast cosmic sprawl originate? The answer may lie in a concept both simpler and stranger: cosmic inflation. Inflation, a period of exponential expansion in the universe's earliest moments, was first proposed to explain the uniformity of the cosmos. Yet, if our universe is but one brain in a higher dimensional bulk, inflation could be the echo of a primordial collision or the stretching of a newly formed membrane. The mathematics of string theory suggest that inflationary fields, hypothetical energy fields driving rapid expansion, might emerge naturally from the dynamics of brains. As we shift our gaze from the geometry of strings to the birth of the universe itself, we enter a realm where speculation and evidence intertwine. The patterns imprinted in the cosmic microwave background, the faint afterglow of the Big Bang, may hold traces of these higher dimensional interactions. Future observations from gravitational wave detectors to deep space telescopes could test these predictions, bridging the gap between theory and reality. For now, the journey continues, a voyage through dimensions unseen toward the origins of time and space. In the earliest moments of existence, before time had a name and space was a concept yet to unfold, the universe underwent a transformation so profound it defies imagination. Picture a single point, infinitely dense and seething with energy, poised on the brink of becoming everything. Then, in the blink of an eye, or rather, in a fraction of a trillionth of a second, the cosmos exploded outward in a surge of expansion, so violent and rapid that it outpaced the speed of light itself. This is cosmic inflation, a fleeting yet epochal event that stretched the fabric of space-time to unimaginable proportions. Imagine a balloon inflating not gently, but with such ferocity that its surface ripples and warps, imprinting patterns into the very essence of reality. These ripples, born of quantum fluctuations frozen into the fabric of the universe during inflation, would later seed the galaxies, stars, and planets we see today. Yet, this is only the beginning of the story, for inflation did not end uniformly across the cosmos. Instead, it gave rise to a phenomenon far stranger than a single universe, a multiverse of infinite complexity, a cosmic foam of bubble universes, each with its own history, its own laws, and its own Big Bang. This vision of the multiverse is not mere speculation, but a natural consequence of the mathematics that govern inflation. Just as a single drop of water can ripple across a pond, so too do the quantum fluctuations of the early universe propagate through the endless inflationary sea. Some regions of this primordial field cool and settle, birthing isolated universes like pearls on a string. Others remain in a state of perpetual inflation, generating new bubbles in an unceasing cascade. The result is a vast fractal-like structure of universes, each separated by a chasm of eternally expanding space. To stand within one such bubble is to gaze into a night sky unaware of the countless other worlds that share this cosmic tapestry. The implications of this model are staggering. Our universe is not unique, nor is it the sum total of existence. It is but one note in a symphony of realities, each playing its own tune in the grand orchestra of the multiverse. Yet, for all its grandeur, this picture remains elusive, hidden behind layers of theoretical abstraction and observational limits. We cannot peer beyond the veil of our own universe, but the echoes of its birth, ripples in the cosmic microwave background, hint at the possibility of something greater. Could these ripples bear the scars of collisions with neighboring bubbles? Might the very structure of space-time contain whispers of parallel worlds? As we delve deeper into the mechanics of inflation, we uncover a cosmos not bound by singularity, but by an infinite expanse of possibility. The journey ahead will take us from the equations of theoretical physics to the philosophical ramifications of a multiverse, where every choice, every law, and every quirk of nature may have a counterpart in another realm. At the heart of cosmic inflation lies a simple yet revolutionary idea. The universe expanded exponentially in its first moments, stretching from subatomic scales to cosmic proportions in an instant. This concept was first proposed by physicist Alan Guth in 1980 as a solution to two perplexing problems in cosmology: the horizon problem and the flatness problem. The horizon problem questions why distant regions of the universe, which have never had time to exchange information due to the finite speed of light, exhibit nearly identical temperatures in the cosmic microwave background. The flatness problem, meanwhile, puzzles over why the density of the universe is so finely tuned to the critical density required for a flat geometry, despite the expectation that small deviations would have been magnified over time. Inflation provides an elegant resolution to both. By positing a period of rapid expansion, it stretches the observable universe to a uniform temperature and flattens its geometry, much like inflating a balloon smooths out wrinkles in its surface. However, the mechanism driving inflation is not as straightforward as a simple burst of expansion. Instead, it relies on a hypothetical scalar field, often referred to as the inflaton field. This field permeates all of space and, in its initial high-energy state, generates a repulsive gravitational force that drives exponential growth. As the field slowly rolls toward a lower energy state, a process known as rolling down the potential energy hill, inflation begins to wane. Yet, due to the probabilistic nature of quantum mechanics, this transition is not instantaneous or uniform. In some regions, the field fluctuates upward, prolonging inflation, while in others it collapses, halting the expansion and triggering a Big Bang. These quantum fluctuations, though minute, become imprinted as density variations in the nascent universe, seeding the large-scale structures we observe today. What makes inflation truly mind-bending is its implication of eternal inflation. In regions where the inflaton field remains in a high-energy state, inflation continues indefinitely, generating new universes in a recursive cycle. This leads to a self-reproducing multiverse, where each bubble universe is born from a localized end to inflation, surrounded by an ever-expanding ocean of inflating space. The mathematical models supporting this scenario are rooted in quantum field theory and general relativity, yet they also introduce paradoxes. For instance, if time is defined within each bubble universe, what meaning does it hold in the eternally inflating regions? Does the concept of causality break down when universes are born in isolation from one another? These questions highlight the boundary between known physics and the speculative frontier of cosmology. The work of physicists like Andre Linde further refined inflationary theory with the concept of chaotic inflation, which posits that inflation can occur in a wide range of initial conditions, making it a generic feature of the universe rather than a rare occurrence. In Linde's framework, the inflation field exists in a landscape of potential energy states, and random quantum fluctuations determine where and when inflation ends. This leads to an infinite number of bubble universes, each with distinct physical constants and laws. While this model elegantly explains the diversity of possible universes, it also raises profound questions about the nature of reality. If every physically possible configuration exists somewhere in the multiverse, does the concept of uniqueness lose its meaning? And if so, what does that imply for our place in the cosmos? To inhabit a single bubble universe is to live in a cosmos that is both familiar and alien. Within our bubble, the laws of physics appear consistent. Gravity binds galaxies into clusters. Electromagnetism governs the dance of atoms, and the standard model of particle physics describes the fundamental particles that compose all matter. Yet, according to eternal inflation, these laws are not universal in the absolute sense. They are local, confined to our particular region of the multiverse. Elsewhere, in other bubbles, the constants of nature may differ. Perhaps the strength of gravity is weaker, or the electromagnetic force is stronger, altering the chemistry of life as we know it. Some universes might lack stable atoms altogether, while others could harbor exotic forms of matter and energy beyond our comprehension. The diversity of possibilities is staggering, limited only by the mathematical constraints of the inflaton field and the quantum fluctuations that seed each bubble. One of the most tantalizing aspects of the multiverse hypothesis is the question of whether we can detect evidence of neighboring universes. If two bubble universes collide, the impact would leave a distinctive imprint on the cosmic microwave background, the relic radiation from the Big Bang. Theorists predict that such a collision would produce a disk-shaped anomaly in the CMB, with a temperature gradient that deviates from the otherwise uniform distribution. Over the past decade, experiments like the Planck satellite have meticulously mapped the CMB, searching for these telltale signs. So far, no definitive evidence has been found, but the absence of a signal is not proof of absence. The challenge lies in distinguishing between a true collision signature and the statistical noise inherent in the data. Moreover, the probability of a collision depends on the relative motion and distance between bubble universes, factors that remain speculative. Even if collisions remain undetected, the multiverse model carries profound philosophical implications. If every possible outcome of a quantum event exists in a separate universe, then the concept of free will becomes entangled with determinism. Every choice you make spawns a new branch of reality, where alternatives play out in parallel. This notion, reminiscent of the many worlds interpretation of quantum mechanics, suggests that the multiverse is not merely a physical structure, but a repository of all possibilities. It challenges our perception of identity, for if there exists a version of you in another universe who made different choices, what defines your uniqueness? Is consciousness confined to a single thread of reality, or does it span the vastness of the multiverse? The inevitability of the multiverse also reshapes our understanding of existence. Eternal inflation implies that the creation of universes is not a singular event, but an ongoing process, with new bubbles forming continuously. This raises the unsettling possibility that our universe is not special but ordinary, one of infinitely many. The Copernican principle, which states that Earth does not occupy a privileged position in the cosmos, extends to the multiverse. We are not the center of creation, nor are we alone in the grander scheme. This perspective humbles us, reminding us that our reality is but a fragment of a larger whole, a fleeting moment in an eternal cosmic drama. Yet, for all its strangeness, the multiverse is not a purely abstract concept. It emerges naturally from the equations of inflationary cosmology, making it a testable hypothesis rather than a philosophical fantasy. Future advancements in observational astronomy, such as detecting gravitational waves from the early universe or identifying non-Gaussian features in the CMB, may provide indirect evidence of the multiverse. Until then, the bubble universe foam remains a theoretical framework, a bridge between the known and the unknown, inviting us to ponder the infinite possibilities that lie beyond the veil of our own cosmos. If the multiverse is a cosmic ocean of bubble universes, what anchors them in place? What prevents these isolated realms from drifting endlessly into the void of eternal inflation? The answer may lie in forces we have barely begun to understand, forces that shape our own universe in ways we are only starting to grasp. Chief among these is dark matter, an enigmatic substance that neither emits nor absorbs light, but exerts a gravitational pull on visible matter. Comprising approximately 27% of the universe's mass-energy content, dark matter is the unseen scaffolding upon which galaxies form and evolve. Yet its true nature remains one of the greatest mysteries in modern astrophysics. Could dark matter be more than a cosmic glue? Could it serve as a bridge between universes, a subtle thread woven through the fabric of the multiverse? Some speculative theories propose that dark matter interacts with other dimensions or fields beyond the standard model, potentially linking our universe to its neighbors. For instance, if dark matter particles originate from the decay of the inflaton field, or from the collision of bubble universes, they might carry signatures of events occurring outside our cosmic horizon. Such ideas remain highly theoretical, but they open the door to a profound possibility that the invisible forces shaping our universe are not confined to its boundaries but resonate across the multiverse. As we turn our gaze inward to study dark matter, we may be peering outward as well, searching for whispers of a reality beyond our own. The next segment of this journey will delve into the shadowy realm of dark matter, tracing its elusive presence through the cosmos and contemplating its role in the grand architecture of existence. Like the ripples of inflation, the secrets of dark matter may reveal connections we have yet to imagine, binding the multiverse together in ways we are only beginning to comprehend. In the vast, silent expanse of the cosmos, there exists an enigma that defies our senses yet shapes the destiny of galaxies. This is dark matter, a spectral force that does not emit, absorb, or reflect light, rendering it invisible to our telescopes. Yet its gravitational pull is undeniable, binding stars and gas clouds into the intricate spirals and elliptical halos we call galaxies. Without it, the universe as we know it would collapse into chaos, its celestial structures unraveling like threads pulled from a tapestry. Dark matter is the ghost of the cosmos, an unseen scaffolding upon which the visible universe is built. But what if this ghost is not merely a relic of our own universe? What if its presence hints at something far stranger, a whisper from another reality, a hand reaching across the veil of existence? The notion that dark matter might originate beyond our universe is both unsettling and exhilarating. It suggests that the fabric of space-time is not a solitary construct, but a multi-dimensional loom, woven with threads from realms we cannot yet perceive. To entertain this possibility is to peer into a mirror and glimpse not one's reflection, but the shadow of a parallel world. The idea is as ancient as curiosity itself. Long before the term dark matter entered scientific lexicon, humans have wondered if their universe was alone. Ancient myths spoke of hidden realms and unseen forces. Now modern science offers a framework to ask these questions with rigor. If dark matter is not just a mystery within our universe, but a bridge to others, then we stand at the threshold of a revelation that could redefine our place in the cosmic order. The universe, already unfathomably vast, may be only one thread in a multiverse, a tapestry of realities stretching beyond imagination. The story of dark matter begins with the motions of galaxies. In the 1930s, Swiss astronomer Fritz Zwicky observed that the Coma cluster of galaxies moved in ways that defied explanation, The visible matter, stars, gas, and dust could not account for the gravitational forces required to keep the cluster from flying apart. Decades later, Vera Rubin's studies of galaxy rotation curves confirmed this anomaly. Spiral galaxies rotated at speeds that implied they contained far more mass than could be seen. Stars at the edges of galaxies, for instance, orbited their centers at velocities that should have flung them into the void. Instead, they clung to their orbits, held in place by an invisible gravitational hand. This missing mass, termed dark matter, constitutes roughly 27% of the universe's total mass energy content. By contrast, ordinary matter, the stuff of stars, planets, and life, accounts for less than 5%. The rest is attributed to dark energy, the mysterious force driving the universe's accelerated expansion. Yet despite its prevalence, dark matter remains elusive. Unlike ordinary matter, it does not interact with electromagnetic forces, meaning it neither emits nor absorbs light. Its existence is inferred solely through its gravitational effects on visible matter, a shadow cast by a phantom. Scientists have proposed numerous candidates to explain dark matter's nature. Among the most prominent are weak In these frameworks, our observable universe is a three-dimensional brain, floating in a vast, multi-dimensional bulk. Just as a two-dimensional creature confined to the surface of a sheet of paper might never notice the third dimension, we might be blind to dimensions beyond our own. If dark matter is composed of particles that exist in these extra dimensions, they would appear to us as ghostly entities present in our gravitational landscape, but imperceptible otherwise. Another compelling line of inquiry comes from the study of gravitational lensing, a phenomenon in which massive objects bend light from distant sources. Observations reveal that the distribution of dark matter often forms vast cosmic webs, connecting galaxy clusters like nodes in a neural network. These structures defy explanation by local physics alone. Could they be shaped by forces originating from adjacent universes? Some models propose that dark matter is not a substance native to our universe, but a projection of interactions occurring in higher dimensions. For example, the so-called mirror universe hypothesis suggests that our universe has a counterpart in a parallel dimension, with dark matter arising from the gravitational influence of its unseen twin. Even the standard model of cosmology, known as the lambda cold dark matter (LSCDM) model, acknowledges gaps that hint at deeper truths. While LSCDM successfully explains large-scale structure formation and the cosmic microwave background, it relies on arbitrary assumptions about dark matter's properties. The absence of a unified theory reconciling general relativity and quantum mechanics further underscores the limits of our current understanding. These cracks in the foundation invite speculation. What if dark matter is not a problem to be solved, but a clue pointing toward a grander multi-dimensional reality? If dark matter is a bridge between universes, the implications ripple outward, challenging every assumption about the nature of reality. Imagine a cosmos where our universe is but one leaf in an infinite tree of realities, each separated by dimensions too small to perceive. In this vision, dark matter becomes the root system, unseen, yet vital to the structure of the whole. Such a perspective reframes the question of existence itself. Are we inhabitants of a single universe, or residents of a multiverse? Our consciousness tethered to one reality among many? The concept of interdimensional dark matter opens doors to profound possibilities. For starters, it could explain phenomena that elude conventional physics. Consider the accelerating expansion of the universe, driven by dark energy. If this force arises not from within our universe, but from interactions with other realities, the expansion might be a tug-of-war between dimensions. In this scenario, dark energy is not an intrinsic property of space, but a manifestation of repulsive gravitational forces from adjacent universes. Such a model could unify dark matter and dark energy under a single framework, resolving one of cosmology's greatest conundrums. Moreover, the existence of interdimensional dark matter could revolutionize our understanding of time and causality. If our universe is interconnected with others, the flow of time might not be absolute but relative to the dynamics of the multiverse. Paradoxes like the grandfather paradox, where a time traveler prevents their own birth, might dissolve if actions in one universe ripple into others, preserving consistency across the ensemble. This perspective aligns with theories such as the holographic principle, which suggests that information about a volume of space can be encoded on its lower dimensional boundary. If true, our universe could be a projection of data stored in a higher dimensional realm, with dark matter serving as the medium through which these realms communicate. The philosophical ramifications are equally staggering. If dark matter is evidence of other universes, it implies that our reality is not unique, but one of countless variations. This realization could diminish humanity's perceived centrality in the cosmos, yet it also elevates the possibility of coexistence with other intelligent beings. Might advanced civilizations in neighboring universes have harnessed interdimensional dark matter to traverse the multiverse? Could their technology rely on manipulating the very threads that bind our reality together? Such speculations push the boundaries of science into the realm of science fiction, yet they are grounded in the same principles that led Einstein to envision a universe warped by gravity. On a more practical level, the exploration of interdimensional dark matter could spur technological breakthroughs. If we learn to detect and manipulate its properties, we might develop methods to probe other universes directly. Instruments designed to measure gravitational waves, ripples in space-time, caused by cataclysmic events, could be repurposed to search for signatures of interdimensional interactions. Similarly, particle accelerators like the Large Hadron Collider might generate micro black holes or exotic particles that hint at higher dimensional physics. Even if such experiments fail, the pursuit itself could yield insights into the fundamental laws governing existence. Yet these possibilities raise ethical and existential questions. If other universes exist, do we have a responsibility to protect them, or even ourselves, from unintended consequences? Could tampering with interdimensional forces destabilize our own reality? The history of science is replete with discoveries that initially seemed benign, but carried unforeseen risks. The harnessing of atomic energy, for instance, brought both medical advancements and the threat of annihilation. As we peer into the multiverse, we must tread carefully, balancing curiosity with caution. Ultimately, the idea that dark matter is interdimensional invites us to reimagine the cosmos as a living, interconnected web. No longer is the universe a static backdrop for our lives, but a dynamic participant in a grander narrative. The invisible threads of dark matter, once dismissed as mere placeholders in our equations, become the sinews of a multiversal body. In this new paradigm, the search for dark matter is not just a quest to solve a cosmic riddle. It is a journey to understand our place in a tapestry of realities, each one a reflection of the others, yet distinct in its own right. As we contemplate the unseen forces that bind our universe to others, our gaze is naturally drawn to the most enigmatic objects in the cosmos: black holes. These regions of space-time, where gravity is so intense that not even light can escape, have long been regarded as cosmic graveyards, places where matter vanishes into oblivion. Yet, if dark matter is a bridge between universes, might black holes serve as the gatekeepers of these connections? Some theories suggest that the extreme curvature of space-time near a black hole could warp the fabric of reality, creating passageways to other dimensions, or even other universes. The notion of black holes as portals is not new. In the 1960s, physicist John Wheeler proposed that the singularity at a black hole's core might give rise to a white hole, a theoretical region where matter is expelled into a different point in space-time. More recently, the ER-EPR conjecture, inspired by the work of Albert Einstein and his colleagues, has suggested that entangled particles are connected by microscopic wormholes. If this connection extends to macroscopic scales, it is conceivable that black holes could be linked to other regions of the universe or other universes altogether through these bridges. As we turn our attention to black holes, we step into a realm where the boundaries between science and speculation blur. What lies beyond the event horizon? Is it a dead end or a doorway to the unknown? The answers may lie in the same invisible threads that weave through dark matter, waiting to be unraveled. Beyond the shimmering veil of the cosmos, where stars burn like ancient sentinels and galaxies spiral in eternal waltz, lies a mystery that defies comprehension: the black hole. A black hole is not merely a void, nor a tomb for light, but a crucible of space-time itself, a place where gravity carves the fabric of existence into spiraling tides. To cross the event horizon is to surrender to a fate so alien to human intuition that even the most advanced mathematics stumbles in its attempt to describe it. Here, time bends backward, space folds inward, and the laws of physics dissolve into abstraction. Yet within this abyss, some scientists whisper of a possibility that transcends annihilation: the notion that black holes may not be endpoints but gateways. What if the singularity at their heart, the point where density becomes infinite and geometry collapses, is not a dead end, but a threshold to something entirely new? What if the black hole, far from being a cosmic eraser, is instead a womb for other realities, birthing universes from the ashes of the old? This idea, though speculative, invites us to peer into the unknown with both trepidation and awe, to imagine a universe not as a closed book, but as an infinite library where every page turns into another story. The very name black hole conjures images of destruction, yet its essence is more enigmatic than its title suggests. It is a region of space-time where the gravitational pull is so intense that nothing, not even the swiftest photon, can escape. The event horizon, its outer boundary, marks the point of no return, a spherical surface that hides all secrets within. But what lies beyond? The equations of general relativity, Einstein's grand synthesis of space and time, predict a singularity at the core of a black hole, a point of infinite density where the known laws of physics break down. Yet this prediction is incomplete, for it ignores the quantum realm, where particles dance in probabilistic uncertainty, and the fabric of reality trembles with subatomic chaos. The interplay between these two pillars of modern physics, relativity and quantum mechanics, reveals a paradox that has haunted physicists for decades. How can something as vast as a black hole, governed by gravity's relentless pull, coexist with the strange flickering world of quarks and wave functions? The answer may lie in the singularity itself, which, rather than being a final collapse, could be the seed of a new beginning. If the singularity is not an end but a transformation, then the black hole becomes more than a devourer. It becomes a creator, a cosmic architect shaping realms we cannot yet fathom. To entertain this idea is to venture into the frontier of theoretical physics, where speculation dances hand in hand with mathematical rigor. The concept of black holes as portals to other realities is not a fantasy born of science fiction, but a hypothesis grounded in the language of equations and thought experiments. Consider the possibility that the singularity is not a single point, but a nexus, an intersection where the threads of multiple universes converge. In this vision, the black hole does not erase information, it transmutes it, encoding it into the architecture of a nascent cosmos. Such a notion challenges the conventional understanding of entropy, the measure of disorder in a system, which suggests that information should never truly vanish. If a black hole destroys information, it would violate a fundamental principle of quantum mechanics. But if the singularity instead redirects information into a parallel dimension, the paradox dissolves. This perspective reframes the black hole as a kind of cosmic recycling bin, transforming the remnants of one universe into the building blocks of another. Yet the leap from theory to reality is fraught with uncertainty. No empirical evidence confirms the existence of such portals, and the extreme conditions near a black hole render direct observation impossible. The event horizon, after all, is a one-way street. Any probe sent to investigate would be torn apart by tidal forces before it could transmit data. Nevertheless, the allure of this idea persists, driven by humanity's insatiable curiosity and the tantalizing possibility that the universe is far stranger than we dare to imagine. The notion of black holes as gateways to other realities invites us to reconsider our place in the cosmos. Are we alone in this vast expanse? Or do our actions ripple across dimensions we cannot perceive? Is every black hole a mirror reflecting alternate histories, or a key unlocking doors to futures yet unwritten? These questions, though unanswered, compel us to gaze beyond the familiar and embrace the sublime mystery of the unknown. At the heart of this exploration lies general relativity, the theory that redefined our understanding of gravity and space-time. Albert Einstein's field equations, formulated in 1915, describe gravity not as a force acting at a distance, but as the curvature of space-time caused by mass and energy. A black hole emerges as a natural consequence of these equations. When a massive star exhausts its nuclear fuel, it can no longer resist the inward pull of gravity, collapsing under its own weight until its core compresses into a singularity. The surrounding space-time warps so violently that it forms an event horizon, a boundary beyond which escape becomes impossible. General relativity predicts that within this horizon, the singularity is a point of infinite density, where the curvature of space-time becomes infinite, and the classical laws of physics cease to function. However, this prediction is inherently incomplete, for it does not account for the quantum nature of the universe. Quantum mechanics, the framework governing the behavior of particles at the smallest scales, introduces a radical tension with general relativity. In the quantum realm, particles exhibit wave-like properties, existing in superpositions of states until measured, and entanglement allows particles to influence each other instantaneously across vast distances. When applied to black holes, these principles give rise to profound paradoxes. One of the most enduring is the information loss problem, first articulated by Stephen Hawking in the 1970s. According to Hawking's calculations, black holes emit radiation, now known as Hawking radiation, as particle pairs form near the event horizon, with one member escaping while the other falls into the singularity. Over time, this process causes the black hole to evaporate, eventually vanishing entirely. The paradox arises because, according to quantum mechanics, information about the infalling matter must be preserved. If a black hole evaporates, what happens to the information it once contained? If it is destroyed, it violates the principle of unitarity, which states that information must always be conserved in quantum systems. The resolution to this paradox remains elusive, but one intriguing possibility is that the singularity does not annihilate information, but instead channels it into another reality. This idea aligns with the no-hair theorem, a principle derived from general relativity stating that black holes can be fully described by only three properties: mass, charge, and angular momentum. All other information about the matter that formed the black hole is lost, as if it were stripped away by the gravitational maelstrom. Yet the no-hair theorem, like the singularity itself, is a product of classical physics and may not hold in the quantum regime. If the singularity is not a true point of infinite density but a quantum fluctuation, a foam of Planck scale structures, then information might not be lost but encoded in the geometry of the singularity. From this perspective, the black hole becomes a repository of information, a cosmic vault where the history of swallowed matter is preserved in a form we cannot yet decipher. Another avenue of exploration is the EREPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind in 2013. This hypothesis posits a deep connection between two seemingly unrelated phenomena: Einstein-Rosen bridges, wormholes, and quantum entanglement, Einstein-Podolsky-Rosen pairs. According to EREPR, entangled particles are linked not just by correlations in their quantum states, but by a physical connection through space-time, a wormhole. If this conjecture holds, then black holes themselves might be entangled with other regions of space-time, effectively forming bridges to distant locations, or perhaps to entirely different universes. In this framework, the singularity is not a dead end, but a nexus where entangled wormholes converge, allowing information to traverse the cosmic fabric. While this idea is still highly speculative, It offers a tantalizing glimpse into the possibility that black holes are not isolated entities, but nodes in a vast network of interconnected realities. The interplay between these theories underscores the limitations of our current understanding. General relativity and quantum mechanics, though both extraordinarily successful in their domains, remain incompatible, and the true nature of the singularity lies at the intersection of these two regimes. To reconcile them, physicists are developing theories of quantum gravity, such as string theory and loop quantum gravity, which attempt to unify the macroscopic and microscopic descriptions of the universe. These frameworks suggest that space-time itself may be discrete at the Planck scale, composed of fundamental units akin to pixels on a screen. If true, then the singularity might not be a point of infinite density, but a complex structure of vibrating strings or loops, where information is neither lost nor destroyed but transformed. In this vision, the black hole becomes a dynamic interface between realities, a cosmic lighthouse guiding matter and energy toward new dimensions. If black holes are indeed portals to other realities, the implications extend far beyond the confines of astrophysics, challenging our understanding of existence itself. Imagine a universe where every dying star gives birth to a new cosmos, a cycle of creation and destruction echoing through the multiverse. In this scenario, the universe is not a static entity but a living organism, perpetually regenerating through the gravitational collapse of its own components. Each black hole then becomes a cosmic womb, where the entropy of one universe is reborn as the order of another. This perspective transforms our perception of time and causality. What appears as the death of a star could be the genesis of a parallel reality, a hidden chapter in the grand narrative of the cosmos. The concept evokes a sense of continuity, suggesting that the universe is not linear but recursive, an endless loop of emergence and dissolution. Such a model raises profound questions about the nature of consciousness and identity. If information is not destroyed, but transmuted across dimensions, could fragments of our own existence persist in these newborn universes? Might there be versions of ourselves, shaped by different histories and choices, thriving in realities we cannot access? The idea of parallel selves is not new. It is central to the many worlds interpretation of quantum mechanics, but the notion that these selves could be physically connected through black holes adds a new layer of intrigue. Perhaps the singularity acts as a conduit, allowing echoes of our decisions to ripple across the multiverse. This possibility blurs the line between observer and observed, between subject and object, and invites us to consider whether our individuality is as fixed as we believe. Moreover, the existence of black holes as portals could revolutionize our approach to space travel and interstellar exploration. While current technology renders traversal of a black hole impossible, the theoretical framework hints at the potential for future advancements. If wormholes, hypothetical tunnels through space-time, can be stabilized and navigated, they might offer shortcuts to distant stars or even other universes. The challenges are immense. The intense gravitational forces near a black hole would require materials stronger than anything currently known, and the stability of a wormhole remains a topic of debate among physicists. Yet the mere possibility ignites the imagination, urging us to envision a future where humanity's reach extends beyond the confines of a single cosmos. In this vision, black holes are not fearsome voids but stepping stones, bridges to uncharted territories where the laws of physics may differ, and new forms of life and intelligence await discovery. The philosophical ramifications of this concept are equally staggering. If the universe is a tapestry woven from countless threads, each representing a distinct reality, then our existence is but one thread among many. This perspective fosters humility, reminding us that our understanding of the cosmos is fragmentary, shaped by the limitations of our senses and the tools we wield. It also compels us to confront the fragility of our reality. If our universe is but one of many, what defines its uniqueness? Is there a purpose to its existence? Or are we simply participants in an infinite game of cosmic chance? The answers may elude us, but the questions themselves are a testament to the boundless curiosity that drives human inquiry. Furthermore, the idea of black holes as gateways invites us to reconsider the nature of time. In classical physics, time is a linear progression, flowing inexorably from past to future. However, within the warped space-time of a black hole, time behaves differently, stretching and bending in ways that defy our everyday experience. The singularity, where time and space collapse into a singularity, may represent a moment outside of time itself, a point where the distinction between cause and effect dissolves. If this is the case, then the portal created by the black hole could lead not only to other spatial locations, but to other temporal frameworks, where time flows in reverse or exists in a state of perpetual stasis. Such a notion challenges our linear conception of existence, suggesting that time is not a universal constant but a variable dependent on the curvature of space-time. The environmental implications of this hypothesis are also worth considering. If every black hole births a new universe, then the universe is in a state of perpetual growth, generating new realities at an exponential rate. This process could explain the accelerating expansion of the cosmos, as the creation of new universes injects energy into the existing framework. Alternatively, it could imply that the universe is not expanding but evolving, shedding old forms and adopting new ones in an endless cycle. Either way, the concept reshapes our understanding of cosmic evolution, positioning black holes as agents of transformation rather than mere endpoints. Yet, for all its grandeur, this idea carries a sobering reminder of the limits of human knowledge. The singularity, with its infinite density and zero volume, remains an enigma, a chasm in our understanding that no equation can fully illuminate. Our instruments, no matter how sophisticated, cannot peer into the heart of a black hole, and our theories, however elegant, are provisional, subject to revision as new evidence emerges. This humbling realization underscores the importance of continued exploration and the pursuit of interdisciplinary collaboration. By uniting the insights of astrophysics, quantum mechanics, and philosophy, we may one day unravel the mysteries of the singularity and determine whether black holes are indeed cosmic gateways or merely the universe's most perplexing enigma. As we contemplate the possibility of black holes as portals to other realities, we find ourselves standing at the edge of a conceptual abyss, gazing into a realm where the boundaries of space, time, and existence blur. This inquiry naturally leads us to another profound question. If the universe is a tapestry of interconnected realities, how do these realities come into being? The answer may lie not in the gravitational collapse of stars, but in the quantum realm, where the act of observation itself shapes reality. Enter the many worlds interpretation, a revolutionary theory that proposes that every decision, every quantum event, spawns a new branch of existence. In this framework, the universe is not a single linear narrative, but an infinite tree of possibilities, each choice fracturing reality into parallel worlds. Just as a black hole may serve as a gateway between universes, the quantum fluctuations of particles may give rise to an ever-expanding multiverse, where every potential outcome of an event plays out in its own distinct reality. The many worlds interpretation, first proposed by physicist Hugh Everett III in 1957, offers a radical departure from the Copenhagen interpretation, which posits that quantum systems exist in superpositions until observed, at which point the wave function collapses into a definite state. In contrast, the many worlds view suggests that all possible outcomes of a quantum measurement actually occur, each unfolding in a separate, non-communicating branch of the universe. This idea aligns with the notion that black holes may not destroy information, but instead encode it into new dimensions, reinforcing the idea that the universe is far more expansive than our immediate perception allows. Just as a black hole could lead to a new cosmos, a quantum event could lead to a new branch of reality, each as real as the last. This transition from the cosmic scale of black holes to the microscopic realm of quantum mechanics underscores the interconnectedness of all things. Both domains challenge our intuitions, revealing a universe that is not static but dynamic, not singular but plural. As we delve deeper into the many worlds interpretation, we will explore how this theory redefines our understanding of identity, free will, and the nature of reality itself. We will examine the implications of an infinite number of parallel universes, each shaped by the choices we did not make, and consider whether these branches are truly separate, or if there exists some hidden symmetry linking them. In doing so, we continue our journey through the cosmos, seeking to unravel the threads that weave together the fabric of existence. In the quiet hum of morning sunlight, filtering through half-closed eyelids, a decision forms a flicker of thought that divides the fabric of reality. You reach for the coffee cup, but in another world, your hand hovers over the steaming teacup instead. You choose to stay at home, yet in an adjacent timeline, you board the plane, your suitcase packed with the scent of adventure. This is not mere imagination, it is the unfolding of the many worlds. Interpretation, MWI, a theory that reimagines the universe not as a single linear path, but as an ever-expanding tree of infinite branches. Every quantum event, no matter how trivial or monumental, spawns a new reality. The act of choosing is not a narrowing of possibility, but an explosion into multiplicity. Here, the universe breathes in tandem with your heartbeat, its vastness unfurling with each moment of uncertainty. To grasp MWI is to relinquish the comforting notion of a singular you and embrace the staggering truth that you are not one person, but an infinite constellation of selves, each navigating their own story in a cosmos that thrives on divergence. This interpretation challenges the very essence of how we perceive time and identity. For millennia, humanity has clung to the idea of a fixed past and a singular present, a narrative thread that winds from birth to death. Yet MWI reveals a deeper, more intricate design, a reality where every possible outcome exists simultaneously, layered like the pages of an endless book. The universe is not a monologue, but a chorus, a symphony of branching paths that defy the limitations of language and logic. Imagine standing at the edge of a forest where every step you take splits the ground beneath you, each division revealing a new trail, each trail a distinct world. In this forest of realities, you are both wanderer and architect, your choices etching new routes into the ever-growing labyrinth. The implications are profound, not only for physics but for the philosophy of existence itself. If every decision spawns a new universe, then the concept of fate dissolves into the mist, replaced by an ocean of potentiality. The universe becomes less a clockwork mechanism and more a living, breathing entity, endlessly reinventing itself through the dance of probability. Yet, for all its elegance, MWI remains a radical departure from conventional thought. It demands that we abandon the comforting idea of a single, objective reality and accept that our perception is but one leaf on an infinite tree. The act of observation, once seen as a passive act, becomes an active force that shapes the cosmos. When you look at the stars, you are not merely gazing at distant light, you are participating in the creation of a multiverse, each photon a whisper from a parallel world. The universe is not static, it is a dynamic fractal structure, constantly splitting and evolving. This realization invites both humility and wonder. We are not isolated beings adrift in a void, but nodes in a vast network of interwoven fates. Our lives, so often defined by the constraints of time and space, are in fact threads in a tapestry so vast that its edges dissolve into the unknown. To embrace MWI is to stand at the precipice of understanding, where science and poetry converge in a shared awe of the infinite. At the heart of the many worlds interpretation lies a bold rejection of the Copenhagen interpretation, which posits that a quantum system exists in superposition until observed, collapsing into a single state. Hugh Everthird, a young theoretical physicist, first proposed MWI in 1957 as a solution to the paradoxes of quantum mechanics. Rather than accepting the collapse of the wave function as an inherent property of nature, Everett suggested that all possible outcomes of a quantum event actually occur, but in separate non-interacting branches of reality. This elegant hypothesis eliminates the need for an arbitrary distinction between observer and observed, replacing the enigmatic collapse with a continuous deterministic evolution of the universal wave function. In this framework, the universe is not a collection of discrete events, but a seamless, unbroken expanse of possibilities, each unfolding in its own domain. To visualize this, consider the classic thought experiment known as Schrödinger's cat. In the traditional interpretation, the cat is simultaneously alive and dead until an observer opens the box. MWI, however, asserts that both outcomes exist in parallel. In one branch, the cat lives, in another, it perishes. The observer too splits into two counterparts, each experiencing a distinct reality, one where the box reveals a living cat, another where it finds a corpse. Crucially, these branches do not merge or interfere with one another. They evolve independently, governed by the same laws of physics, but separated by the quantum states they inhabit. This absence of communication between branches means that, from within any given universe, the other possibilities remain hidden like parallel rivers flowing alongside one another without ever meeting. The mathematics underpinning MWI is rooted in the Schrödinger equation, which describes how quantum systems evolve over time, unlike the Copenhagen interpretation, which introduces a discontinuous collapse. MWI adheres strictly to the unitary evolution of the wave function. This approach aligns with the principle of quantum coherence, where the total probabilities of all possible outcomes sum to 1. However, the sheer scale of this multiplicity raises a question. How can an infinite number of branches coexist without violating conservation of energy or mass? The answer lies in the nature of quantum states themselves. In MWI, the splitting of realities does not require additional physical resources. Instead, it emerges naturally from the entanglement of particles with their environment. When a quantum system interacts with a macroscopic object, such as a measuring device, the two become entangled, and their combined state evolves into a superposition of correlated results. This process, known as decoherence, effectively isolates each branch from the others, making them inaccessible to one another. Thus, the universe does not grow heavier with each split. It simply becomes more complex, its structure deepening rather than expanding in volume. What makes MWI particularly compelling is its ability to reconcile quantum mechanics with the deterministic framework of classical physics. By eliminating the need for an external observer to collapse the wave function, it restores a sense of objectivity to the universe. In this view, reality is not a fragile construct dependent on human perception, but a robust, self-sustaining system where every possibility is equally real. The act of observation is merely a subjective experience, a perspective embedded within one of the countless branches. This perspective challenges the anthropocentric bias that has long shaped scientific inquiry, suggesting that consciousness is not the arbiter of reality, but a participant in its unfolding. The universe, in its raw form, is not mysterious because it is unknowable. It is mysterious because it is infinite, its depths beyond the reach of any single mind. If every quantum event spawns a new universe, then the implications for identity and agency are staggering. Consider the self. In one branch, you might be a renowned scientist, your name etched into the annals of history. In another, you could be a recluse, content with the quiet rhythm of a solitary life. In yet another, you may never have been born at all. These versions of you are not figments of imagination, but fully realized individuals, each with their own memories, emotions, and aspirations. The existence of such counterparts forces a re-examination of what it means to be you. Is the self a singular entity, or a mosaic of infinite variations? If every choice you make creates a new version of yourself, does free will truly exist, or is it merely the illusion of selecting one path among many? The philosopher David Lewis once described possible worlds as ways things could have been, but in MWI, these worlds are not hypothetical, they are actual, coexisting with ours. The self, therefore, is not a fixed point, but a dynamic, branching structure, its shape determined by the interplay of chance and choice. The emotional weight of this multiplicity cannot be overstated. Imagine knowing that somewhere, in an alternate reality, you made a different decision and lived a vastly different life. Perhaps in one world, you married someone else, or pursued a career you once dreamed of but abandoned. Perhaps in another, you faced a tragedy you narrowly avoided here. The knowledge of these divergent lives raises profound questions about regret, identity, and purpose. Are we defined by the sum of our choices, or by the infinite tapestry of what might have been? The poet Rumi once wrote, "You are not a drop in the ocean, you are the entire ocean in a drop." In the context of MWI, this sentiment takes on new meaning. Every individual is both a single drop and the vast ocean itself, a microcosm of an infinite multiverse. The burden of this realization is immense, yet it also carries a strange comfort. If every possible outcome exists, then perhaps there is no failure, no loss, no irreversible mistake, only a branching path that leads to a different destination. Beyond the philosophical ramifications, MWI also invites speculation about the future of technology and its potential to bridge the gap between these parallel worlds. While current physics suggests that communication between branches is impossible due to the principle of decoherence, some theorists entertain the possibility of indirect interaction. Quantum entanglement, for instance, allows particles to remain correlated regardless of distance, a phenomenon Einstein famously referred to as spooky action at a distance. Could this entanglement extend beyond the confines of a single universe? If so, might future advancements in quantum computing or gravitational manipulation reveal subtle echoes of other branches? The idea is tantalizing but fraught with uncertainty. Even if such communication were theoretically possible, the practical challenges would be astronomical. The energy required to manipulate quantum states on a macroscopic scale, let alone to detect signals from a parallel universe, is currently beyond the limits of human capability. Yet, as history has shown, what seems impossible today may become a frontier tomorrow. Perhaps the most unsettling aspect of MWI is its implications for determinism and free will. If every possible outcome occurs in some branch, then is the concept of choice an illusion? Does the universe merely simulate the appearance of decision-making, with all paths already laid out in the grand design of the multiverse? This line of reasoning echoes the ancient debate between free will and predestination, but with a twist. In MWI, every choice is real, yet none is uniquely privileged. The paradox lies in the fact that while you are free to choose, your choice is not the sole determinant of your future. It is one of many. This duality is both liberating and disorienting. On one hand, it removes the burden of absolute responsibility, offering the reassurance that every alternative path has been taken. On the other, it strips away the certainty of a singular destiny, leaving one adrift in an ocean of possibilities. The human mind, evolved to seek patterns and meaning, struggles to reconcile with the chaos of infinite outcomes. Yet perhaps this struggle is itself a reflection of the universe's nature, a cosmos that thrives on contradiction, where order and disorder coexist in a delicate, ever-shifting balance. As we navigate the labyrinthine corridors of MWI, a new question emerges. Why does our universe possess the precise set of physical laws that allow for the existence of life? The fundamental constants of nature, the strength of gravity, the charge of an electron, the expansion rate of the cosmos, are finely tuned to an almost miraculous degree. If any of these values were slightly different, stars would fail to ignite, atoms would unravel, and the universe would be a barren void. This apparent fine-tuning has led scientists and philosophers to ponder whether such precision is the result of design, chance, or something altogether different. Enter the Anthropic principle, a concept that seeks to explain why our universe appears so hospitable to life. At its core, the Anthropic principle suggests that our observations of the universe must be compatible with the conditions necessary for our existence. In other words, we find ourselves in a universe that allows for life, because if it didn't, we wouldn't be here to ask the question. But this explanation, while elegant, raises further complexities. Does the Anthropic principle merely describe our position within the multiverse, or does it hint at a deeper, perhaps intentional structure to reality? If the many worlds interpretation is correct, and every possible configuration of physical laws exists in some branch of the multiverse, then our universe is but one of countless others, each with its own unique set of rules. Most of these universes would be sterile, incapable of supporting even the simplest forms of life. Yet, by sheer statistical necessity, a few would possess the right combination of constants to give rise to galaxies, planets, and perhaps even conscious observers. From this perspective, the fine-tuning of our universe is not a mystery, but a natural consequence of the multiverse's vast diversity. The Anthropic principle in this light becomes less a statement about the universe, and more a reflection of the observer's bias. We are here because the universe allows us to be here. However, this reasoning does not fully resolve the enigma. The sheer improbability of our universe's parameters still lingers, a shadow at the edge of comprehension. Why, among the infinite possibilities, Did the laws of physics settle into the particular arrangement that permits life? Is it enough to say that we observe this universe because we exist within it? Or does the answer lie in a more profound symmetry yet to be discovered? The search for an underlying principle that governs the multiverse, whether it be a mathematical elegance, a hidden algorithm, or a cosmic imperative, remains one of the greatest frontiers of modern science. As we turn our gaze from the branching realities of MWI to the Anthropic principle, we are reminded that the universe is not only vast in scale but also in depth, a riddle wrapped in the fabric of space-time, waiting to be unraveled. In the vast, silent expanse of the cosmos, there exists a peculiar and almost unsettling harmony. The universe is not merely indifferent to life, it is in many ways designed for it. Consider the gravitational force, the invisible thread that binds planets to stars, stars to galaxies, and galaxies to one another. If gravity were just a fraction stronger, stars would collapse under their own weight before they could ignite fusion, leaving the cosmos dark and barren. Conversely, if it were weaker, matter would disperse too quickly for galaxies to form at all. Similarly, the cosmological constant, a term in Einstein's equations representing the energy density of empty space, must be precisely balanced. A slightly larger value would cause the universe to expand so rapidly that galaxies, let alone planets or life, could never coalesce. These are not mere curiosities. They are razor-thin edges upon which the possibility of existence balances. The universe, it seems, is a delicate instrument, and we are its resonant note. This observation gives rise to a profound question. Is the universe's apparent fine-tuning for life an extraordinary coincidence, or does it hint at a deeper, perhaps intentional structure? The Anthropic principle emerges from this conundrum, offering a framework to grapple with the paradox of our existence. To ponder it is to stand at the intersection of science and philosophy, where the cold equations of physics meet the warm breath of human curiosity. The principle does not merely ask why the universe is the way it is. It challenges us to consider whether our very presence is a necessary condition for the universe to be observed at all. As we peer into the abyss of cosmic history, we find ourselves staring back not as passive spectators, but as active participants in the story of existence. Yet the universe does not yield its secrets easily. For every answer the Anthropic principle provides, it raises new questions. What does it mean to observe a universe? And why does observation seem to shape reality? Are we the product of an infinite lottery, drawn from the multiverse's endless variations? Or do we occupy a privileged position in a singular, purposeful design? These inquiries transcend the boundaries of empirical science, venturing into the realm of metaphysics. But even within the confines of known physics, the principle compels us to confront the staggering improbability of our existence. The universe may be vast, but life is a needle in a cosmic haystack, a fragile, fleeting phenomenon that defies the odds. And yet here we are, gazing upward at the same stars that birthed us, asking why. At its core, the Anthropic principle is a simple yet deceptively profound assertion. The universe must possess properties that allow for the existence of observers, because otherwise, no one would be around to observe it. This idea, first articulated in the 1970s by physicist Brandon Carter, has since evolved into a spectrum of interpretations, each grappling with the implications of our cosmic vantage point. The most straightforward version, often called the weak Anthropic principle, WEP, is a tautology wrapped in a cosmic cloak. It states that the conditions we measure in the universe, such as the values of physical constants or the distribution of matter, are not arbitrary. They are constrained by the requirement that life capable of observing them must exist. In essence, WEP reminds us that the universe is not a blank slate. It is filtered through the lens of our own existence. However, the principle becomes more contentious when extended to the strong Anthropic principle, SAP, which posits that the universe must be such that life will emerge. This formulation implies a kind of cosmic inevitability, a suggestion that the laws of nature are not random, but are instead calibrated to produce observers like us. Some interpretations of SAP even go further, proposing that the universe is aware of its capacity for life, or that it evolves toward the emergence of consciousness. These ideas, while speculative, underscore the philosophical depth of the principle. They challenge the traditional notion of a universe governed purely by indifferent physical laws, replacing it with a narrative in which life plays a central, perhaps even necessary role. The most radical and scientifically fertile interpretation of the anthropic principle arises in the context of the multiverse, a hypothetical ensemble of countless universes, each with its own unique set of physical constants and laws. In this framework, the fine-tuning of our universe is not a miracle but a statistical inevitability. Imagine an infinite ocean of universes, each a distinct bubble in the fabric of reality. Most of these bubbles would be sterile, their physical parameters incompatible with the formation of stars, planets, or complex chemistry. Yet, in the infinitesimal fraction where conditions align for life, observers like us inevitably arise. From our perspective, the universe appears fine-tuned because we cannot exist in any other kind of universe. This is the essence of the weak anthropic principle applied to the multiverse. We find ourselves in a universe that supports life not because it was designed for us, but because we could not exist elsewhere. The multiverse hypothesis, though still unverified, offers a compelling resolution to the fine-tuning problem. It sidesteps the need for a designer or a purposeful force by invoking sheer scale. In an infinite multiverse, every conceivable combination of physical constants exists somewhere, and we happen to inhabit one of the rare universes where the dice fell in our favor. This perspective aligns with the principles of quantum mechanics and cosmological inflation, which suggest that our universe is but one of many in an ever-expanding cosmic foam. While the multiverse remains a theoretical construct, its explanatory power is undeniable. It transforms the seemingly improbable into the statistically certain, grounding the anthropic principle in the language of probability rather than purpose. Yet, even within this framework, the principle raises unsettling questions. If the multiverse is real, what determines its rules? Is there a meta-law governing the generation of universes? Or is the multiverse itself a brute fact of existence? Moreover, how can we test the multiverse hypothesis if we are confined to a single observable universe? These challenges highlight the boundary between science and speculation. The anthropic principle, in its various forms, serves as a bridge between these realms, inviting us to explore the limits of knowledge while acknowledging the humbling truth that our observations are always shaped by our existence. The anthropic principle forces us to confront a paradox at the heart of modern cosmology. The universe appears to be both arbitrary and inevitable. On one hand, the values of fundamental constants such as the strength of the strong nuclear force or the mass of the electron seem randomly assigned, with no obvious reason for their specific magnitudes. On the other hand, these same values are precisely what allow carbon-based life to flourish, suggesting a hidden coherence to the cosmos. This duality has fueled centuries of debate among scientists, philosophers, and theologians, each seeking to reconcile the universe's apparent indifference with the emergence of meaning. One school of thought interprets the anthropic principle as evidence of a cosmic design. Proponents argue that the precision required for life to exist is so astronomically unlikely that it demands an explanation beyond mere chance. In this view, the universe's fine-tuning is akin to a message encoded in the fabric of reality, a signature left by a creator who intended for life to arise. This interpretation resonates with religious and spiritual traditions, which have long viewed the cosmos as a testament to divine artistry. However, it also risks conflating correlation with causation. Just because the universe allows for life does not necessarily mean it was created for life. The multiverse hypothesis, by contrast, offers a secular alternative, framing the apparent design as an illusion born of selection bias. In an infinite ensemble of universes, it is statistically guaranteed that at least one will support life, and we are merely inhabitants of that rare, fortunate corner of the multiverse. Beyond the question of design, the anthropic principle challenges our understanding of purpose. If we are the result of a cosmic lottery, does that diminish our significance? Or does it elevate our role as the sole conscious witnesses to the universe's grandeur? The principle compels us to reconsider the anthropocentric view that places humans at the center of creation. Instead, it positions us as accidental byproducts of a process that has no inherent goal. Yet, this accidentalism does not negate the beauty or mystery of existence. If anything, it underscores the audacity of life emerging from the void, a phenomenon so improbable that it becomes poetically meaningful in its own right. The principle also reshapes our perception of the multiverse itself. By positing that the universe we inhabit is but one of countless others, it dissolves the illusion of uniqueness. In this framework, the laws of physics are not universal truths, but local accidents, valid only within our particular bubble of reality. This realization is both liberating and humbling. It frees us from the burden of seeking absolute answers, while reminding us that our knowledge is forever limited to our cosmic neighborhood. At the same time, the multiverse raises profound questions about the nature of existence. If every possible universe exists, does that include universes where we do not? Does the absence of observers in those universes render them meaningless, or are they equally real regardless of their emptiness? These questions blur the line between science and philosophy, challenging us to define what it means to exist in a multiversal context. Perhaps the most enduring implication of the Anthropic principle is its impact on the search for a unified theory of everything. Physicists have long sought to derive the values of fundamental constants from first principles, hoping to uncover a single equation that governs the universe. The principle, however, suggests that some constants may not be derivable at all. They may simply be contingent properties of our universe, selected by the requirement that life can exist. This idea, though controversial, has gained traction in recent decades, as attempts to unify general relativity and quantum mechanics have yielded no definitive answers. If the constants of nature are not fixed but variable across the multiverse, then our task as scientists shifts from discovering immutable laws to mapping the landscape of possibilities. In this sense, the Anthropic principle may not be a dead end but a new frontier, guiding us toward a deeper understanding of the cosmos. Ultimately, the Anthropic principle invites us to embrace uncertainty. It acknowledges that some aspects of the universe may be unknowable, not because they lie beyond the reach of science, but because they are inherently tied to the observer. Our quest to understand the cosmos is not a linear journey toward absolute truth, but a recursive exploration in which the act of observation shapes the questions we ask. This self-referential loop, the universe observing itself through human consciousness, is both a scientific puzzle and a philosophical revelation. It reminds us that the pursuit of knowledge is not just about discovering the universe, but about discovering ourselves within it. If the universe is a stage upon which life emerges through a combination of chance and necessity, what unseen forces govern the drama of its unfolding? The answer lies in the relentless march of entropy, the measure of disorder in the cosmos. While the Anthropic principle addresses the conditions that allow for life, it does not explain the directionality of time or the progression from order to chaos. These phenomena are encoded in the second law of thermodynamics, which dictates that entropy tends to increase over time. This law is not a rule imposed from above, but a statistical inevitability arising from the sheer number of ways disorder can manifest, compared to order. Yet the connection between entropy and the arrow of time remains one of the deepest mysteries in physics. How does the universe, born from a state of near-perfect uniformity, give rise to the complexity of galaxies, stars, and life itself? And what role does entropy play in shaping the future of existence? As we turn from the question of why the universe is the way it is to the question of why it unfolds as it does, we enter a new realm of inquiry, one that bridges the microscopic dance of particles with the macroscopic sweep of cosmic evolution. The next segment will explore the enigmatic relationship between entropy, time, and the emergence of complexity, revealing how the universe's journey from simplicity to diversity is not a contradiction of the second law, but a testament to its profound implications. In doing so, we will come to see that the same forces that drive the universe toward entropy also create the conditions for life, weaving together the threads of order and chaos into the tapestry of existence. The universe, in its vast and intricate expanse, unfolds as a grand cosmic tapestry woven with threads of order. At its heart lies one of nature's most profound principles, entropy, the measure of disorder within a system. While the laws of physics govern the behavior of matter and energy, it is entropy that imparts a distinct direction to the passage of time. Unlike the reversible equations of Newtonian mechanics, the second law of thermodynamics asserts an irreversible progression toward increasing entropy. This fundamental principle underpins our perception of time's relentless forward motion, shaping the very fabric of existence. Yet, this seemingly inevitable march toward disorder raises an enigmatic question. Why did the universe begin in such a state of extreme order, with minimal entropy, only to evolve into the complex, chaotic cosmos we observe today? The answer may lie in the peculiar conditions of the Big Bang. At the moment of creation, the universe was a singular point of unimaginable density and temperature. Yet paradoxically, it possessed an extraordinary low level of entropy. This initial state defies conventional intuition, as such a highly ordered configuration is statistically improbable. If entropy tends to increase over time, then the early universe must have been in an unusually rare and specific condition, one that has puzzled physicists for decades. Some argue that the low entropy of the early universe is a boundary condition imposed by the laws of physics themselves, while others suggest it may be a consequence of a deeper cosmic framework beyond our current comprehension. Either way, the asymmetry between the past and future remains a cornerstone of our understanding of time. Beyond our own universe, the concept of entropy takes on even greater intrigue when considering the possibility of a multiverse, a vast ensemble of universes, each governed by its own physical laws and initial conditions. In such a scenario, the arrow of time may not be universal, but rather contingent upon the unique properties of each cosmos. Some universes might exhibit entropy increasing in one direction, while others could experience a reversal of this process, leading to a time that flows backward rather than forward. This notion challenges our deeply ingrained perception of time's unidirectional nature, and invites us to contemplate a reality far more diverse and enigmatic than we can presently fathom. As we delve further into the nature of entropy and the arrow of time, we may uncover clues that bridge the gap between the known and the unknown, offering glimpses into the cosmic architecture that governs all existence. At the core of our understanding of time's forward progression lies the second law of thermodynamics, which states that the total entropy of an isolated system never decreases over time. This law governs the transformation of energy and the evolution of systems from order to disorder, establishing a clear distinction between past and future. Consider a simple example. A glass of ice water left on a table will gradually warm as heat transfers from the surrounding air to the ice, causing it to melt. This process is irreversible. Once the ice has melted, it cannot spontaneously reform without external intervention. The same principle applies on a cosmic scale, where the universe itself is an isolated system undergoing an inexorable increase in entropy. This fundamental law is not merely a statistical tendency, but a defining feature of the universe's temporal structure. The Big Bang marks the beginning of this journey, with the universe emerging in a state of remarkably low entropy, an almost perfect equilibrium of energy and matter. From this primordial singularity, the universe expanded, and as it did, entropy increased. Galaxies formed, stars ignited, and planets coalesced, all driven by the interplay of forces and the dissipation of energy. Over billions of years, these processes have led to the complex structures we observe today, each step accompanied by a rise in entropy. The arrow of time, therefore, is not a mere illusion, but a direct consequence of the universe's thermodynamic evolution. Yet the question persists: why did the universe begin in such an exceptionally ordered state? This conundrum has led physicists to explore theories beyond classical thermodynamics, seeking answers in the realm of cosmology and quantum gravity. One prominent hypothesis involves the concept of eternal inflation, a theoretical extension of the inflationary model that suggests the universe is part of a much larger, ever-expanding multiverse. According to this framework, our universe is just one of many bubble universes, each born from quantum fluctuations in a primordial vacuum. In such a scenario, the initial low entropy of our universe may not be a unique anomaly, but rather a natural consequence of the conditions under which it formed. In this multiversal context, the arrow of time may not be uniform across all universes. Just as our universe exhibits an increase in entropy from the Big Bang onward, other universes could possess different entropy gradients, potentially resulting in a reversal of time's direction. Imagine a neighboring bubble universe where entropy decreases rather than increases, where stars collapse into dense, ordered structures instead of dispersing their energy, and where the past appears to emerge from the future. In such a universe, the flow of time would appear inverted to observers within it, challenging our conventional understanding of causality and temporal progression. These speculative ideas, though difficult to verify with current observational tools, offer a compelling glimpse into the broader possibilities of cosmic existence. As we consider these implications, we are reminded that the universe operates according to rules that extend far beyond our immediate perception. The second law of thermodynamics, while seemingly straightforward in its application to everyday phenomena, reveals deep connections between entropy, time, and the fundamental nature of reality. By exploring the origins of entropy and the potential diversity of time's direction across the cosmos, we edge closer to unraveling some of the greatest mysteries of existence. If the arrow of time is dictated by the increase of entropy, then the possibility of universes where entropy decreases rather than increases opens up a fascinating paradox. In such hypothetical realms, the flow of time would appear to move in the opposite direction from what we experience. To an observer in a high-entropy universe, the past would resemble what we perceive as the future, events unfolding in reverse, memories forming before experiences occur, and cause preceding effect. This inversion of time's direction challenges the very foundation of our understanding of causality, raising profound questions about the nature of history, consciousness, and the human experience of time. Consider the implications for an intelligent species inhabiting a universe where entropy decreases over time. In our world, life emerges from disorder, evolving through the accumulation of complexity and information. Organisms grow, learn, and adapt as they consume energy and increase entropy in their surroundings. However, in a universe where entropy diminishes, life might take an entirely different form. Instead of consuming energy to sustain itself, organisms could theoretically release energy as they develop, their structures becoming more refined and ordered with each passing moment. Memory might not be a record of the past, but a premonition of events yet to unfold, as the mind constructs recollections based on future occurrences. In such a reality, the sensation of time moving forward would be an illusion, just as our perception of time flowing from past to future is shaped by the thermodynamic gradient of our own universe. This radical reversal of time's direction also calls into question the very nature of history. In our universe, history is a sequence of events progressing from the past to the present, each moment building upon the last. The past is fixed, the future uncertain, and the present serves as the bridge between them. However, in a universe where entropy decreases, the roles of past and future would be reversed. The future would be a state of higher order, a culmination of all possible outcomes converging into a single, predetermined endpoint. The past, in contrast, would be a chaotic, disordered state from which events unfold in reverse. In such a cosmos, history might not be a record of what has already happened, but a blueprint of what is yet to come, with individuals perceiving their lives as a journey from uncertainty towards certainty. The concept of free will, so central to our understanding of agency and choice, would be fundamentally altered if the future is already determined and entropy naturally decreases. Then all actions might be seen as unfolding in a preordained sequence, devoid of true spontaneity. The implications for perception and cognition are equally profound. Human memory is intrinsically tied to the thermodynamic arrow of time. We remember the past because information is stored in increasingly disordered states, while the future remains uncertain. A being in a high-entropy universe, where entropy decreases over time, might experience memory in an entirely different manner. Rather than retaining images of past events, such a being might generate memories of events that have yet to transpire, constructing a sense of history from the future outward. This inversion of the psychological arrow of time would profoundly alter the way consciousness functions, making it difficult, if not impossible, to distinguish between recollection and anticipation. Moreover, the notion of cause and effect would be fundamentally transformed in a universe where time flows in reverse. In our world, causes precede effects. An action leads to a consequence, and events follow a logical sequence. However, in a universe where entropy decreases, the reverse would be true. Effects would precede causes, with consequences shaping the actions that lead to them. Imagine witnessing an object shatter into pieces before observing it fall from a height, or seeing a tree wither before noticing the roots decay beneath the soil. Such a perspective would challenge the intuitive logic that underpins our understanding of the physical world, forcing us to reconsider the nature of reality itself. Even more intriguingly, the interaction between such a universe and our own raises the possibility of paradoxes and contradictions. If two civilizations, one in a low-entropy universe and the other in a high-entropy universe, were to communicate or encounter one another, they would likely experience one another's perception of time as nonsensical. To inhabitants of our universe, the beings from the high-entropy world would appear to move backward through time, their actions unfolding in reverse. Conversely, those from the high-entropy universe would see us as moving in the opposite direction, our lives progressing from order to chaos. This mutual incomprehension would create a fundamental barrier to communication, as the very concept of time's direction is embedded in the cognitive structures of both species. Such a scenario underscores the profound relativity of time, challenging the assumption that time is an absolute, universal constant. Instead, time may be a local phenomenon, dependent on the thermodynamic properties of a given universe. The direction in which entropy increases or decreases determines the flow of time for observers within that space, shaping their perception of history, causality, and the passage of moments. This realization not only reshapes our understanding of the cosmos, but also invites us to reconsider our place within it. If time is not a fixed dimension but a fluid property of the universe, then our experience of it may be far more limited than we can currently imagine. As we contemplate these possibilities, we are drawn to the deeper question of whether time, as we know it, is truly intrinsic to the universe, or merely a product of the particular conditions that gave rise to our existence. The arrow of time may not be a universal law, but a contingent feature of our universe's initial state, a consequence of the Big Bang's extraordinary symmetry and the subsequent evolution of entropy. If this is the case, then the very fabric of reality may be far more malleable than we assume, and the nature of time may vary across the vast expanse of the multiverse. In such a cosmos, the boundaries between past and future, between cause and effect, may not be as rigid as they appear, opening the door to a reality where time is not a fixed path, but a dynamic, ever-changing construct shaped by the thermodynamic forces that govern each universe. As we grapple with the vast implications of entropy and the arrow of time, we arrive at a question that blurs the line between science and philosophy. Could our entire existence be nothing more than a simulation, a digital construct operating within the framework of another universe? The idea that reality might be an artificial construct is not new. It has long been a subject of speculation in both scientific inquiry and philosophical thought. From Descartes' meditations on the nature of truth to modern computational theories, the notion that our perceived universe could be a programmed illusion has gained renewed interest in light of recent advancements in physics and computer science. If time is not an inherent property of the cosmos, but a function of entropy and thermodynamic gradients, then the very fabric of reality may be far more malleable than we once believed. In the context of the multiverse, this question takes on even greater significance. If entropy can dictate the direction of time in different universes, and if our universe is but one among countless others, could it be that some of these universes are not physical entities in the traditional sense, but rather computational models running within a higher dimensional reality? The simulation hypothesis, first popularized by philosopher Nick Bostrom, posits that it is statistically probable that any sufficiently advanced civilization would eventually create simulated realities indistinguishable from the real world. If such simulations exist, and if we are living within one, then the laws of physics, including the arrow of time, may not be fundamental truths but programmed constraints designed to mimic the behavior of a natural universe. This line of reasoning leads us to an unsettling, yet tantalizing possibility that our reality is not bound by the limitations of entropy and thermodynamics, but is instead shaped by the parameters of an underlying computational framework. In such a scenario, time may not be a continuous flow dictated by entropy, but a discrete sequence of events generated by an algorithmic process. The apparent irreversibility of time could be an emergent property of the simulation's design, ensuring that participants experience a coherent and stable environment. If this is the case, then our understanding of entropy, causality, and the passage of time may be fundamentally misguided, constrained by the artificial rules of a system we have yet to fully comprehend. As we transition from the study of entropy and the arrow of time to the enigma of simulation, we find ourselves standing at the threshold of an even greater mystery, the true nature of reality. What if the universe we inhabit is not a self-contained entity, but a construct within a vaster, unseen framework? What if the fundamental laws that govern our existence are not intrinsic to the cosmos, but are instead the result of an intelligence beyond our comprehension? These questions, while speculative, are grounded in the same scientific and philosophical traditions that have guided our exploration of the cosmos. They challenge us to consider that our perception of time, entropy, and the universe itself may be only a fraction of a far greater, more intricate reality waiting to be uncovered. The universe stretches before us like an unfathomable canvas, a glittering tapestry of stars, galaxies, and unseen forces that govern the very fabric of reality. For millennia, humans have gazed upward, pondering the nature of existence, seeking meaning in the vast expanse beyond our world. What if, at the heart of this grand cosmic mystery, lies an even greater revelation, one that challenges everything we think we know about consciousness, time, and space? The simulation hypothesis, a provocative idea rooted in both philosophy and science, offers just such a challenge. It proposes that what we perceive as reality may not be the fundamental truth, but rather a carefully constructed illusion, a simulation, if you will, created by an advanced civilization beyond our comprehension. At first glance, the notion that we might be living inside a computer-generated universe may seem like the stuff of science fiction. Yet, as our understanding of the cosmos deepens and our technological capabilities evolve, this once fantastical concept begins to take on a more tangible form. Consider the staggering computational power required to simulate a universe as complex as our own, with its billions of galaxies, trillions of stars, and countless planetary systems. If such a feat were possible, then the sheer scale of existence suggests that perhaps the number of simulated universes could vastly outnumber the real ones. If this is the case, the probability that we are living in a simulated reality becomes not just plausible, but perhaps even overwhelmingly likely. Modern science has already laid the groundwork for this hypothesis. Quantum mechanics reveals that the universe operates on a deeply mathematical foundation, with particles behaving in ways that resemble computational processes. Additionally, the holographic principle, a theory in theoretical physics, suggests that all the information contained within a volume of space can be represented as a two-dimensional surface, much like a hologram. These findings hint at a reality that may be fundamentally informational, raising the possibility that we live in a system governed by rules akin to those of a computer program. As we explore this idea further, we are drawn into a realm where the line between simulation and reality blurs. If we are indeed living within a simulation, who or what created it? And more importantly, what does that mean for our perception of free will, consciousness, and the nature of existence itself? These questions, though daunting, are not insurmountable. They invite us to reconsider the very essence of our being and to contemplate the possibility that the universe we inhabit is not merely a backdrop for our lives, but a carefully crafted construct, an intricate simulation waiting to be unraveled. At the heart of the simulation hypothesis lies a thought experiment proposed by philosopher Nick Bostrom, which presents a compelling argument for the likelihood of our reality being a simulation. Bostrom's reasoning is grounded in a simple yet profound observation. If a sufficiently advanced civilization possesses the technological capability to simulate entire universes, it is statistically probable that the number of simulated realities would far exceed the number of base or natural universes. This leads to what Bostrom calls the simulation trilemma, a logical framework that outlines 3 possible scenarios regarding the existence of simulated realities. First, it is unlikely that a civilization will reach a post-human stage capable of running such simulations. Second, even if such civilizations do emerge, they may choose not to create ancestor simulations. This trilemma is particularly compelling because it hinges on the assumption that advanced civilizations will inevitably pursue the development of simulation technologies. Given the exponential growth of computational power over time, as described by Moore's law, it is reasonable to expect that future civilizations will possess the means to generate highly sophisticated simulations indistinguishable from reality. If such simulations become commonplace, the sheer number of simulated universes would dwarf the relatively small number of original universes. By extension, the probability that any given observer, such as ourselves, exists within a simulation becomes astronomically high. This line of reasoning, while unsettling, is logically sound and has led many scientists and philosophers to entertain the possibility that our universe is in fact a simulation. Moreover, modern physics provides additional support for the simulation hypothesis. One of the most striking aspects of quantum mechanics is its computational nature. At the quantum level, particles behave in ways that resemble information processing, suggesting that the fabric of reality may be built upon a fundamental computational structure. The double-slit experiment, for instance, demonstrates that particles exhibit wave-like behavior until observed, at which point they collapse into a definite state. This phenomenon bears a striking resemblance to the way a computer renders a scene only when necessary, optimizing resources by calculating details at the moment of observation. Furthermore, the concept of quantum entanglement, where particles remain connected regardless of distance, mirrors the way information is processed and transmitted across a network, reinforcing the idea that the universe may operate under computational principles. In addition to quantum mechanics, the holographic principle offers another layer of support for the simulation hypothesis. This theory, derived from string theory and black hole thermodynamics, posits that all the information contained within a 3-dimensional volume of space can be encoded on a 2-dimensional surface, much like a hologram. This suggests that our seemingly 3-dimensional universe may be a projection of a lower dimensional reality, akin to a digital rendering generated by a computational system. If the universe functions as a hologram, then it is not unreasonable to consider that it might also function as a simulation, with its physical laws emerging from an underlying computational framework. Taken together, these scientific and philosophical insights lend credence to the idea that we may be living within a simulation. While the notion remains speculative, the convergence of computational theory, quantum mechanics, and the holographic principle creates a compelling case for considering the simulation hypothesis as more than just a theoretical curiosity. As we continue to probe the nature of reality, we must ask ourselves whether the universe we perceive is truly the fundamental reality, or merely a carefully constructed illusion, an intricate simulation waiting to be decoded. If we accept the possibility that our universe is a simulation, a cascade of profound questions emerges, challenging our understanding of existence, consciousness, and the very nature of reality. One of the most immediate implications is the apparent computability of the universe. From the smallest quantum fluctuations to the vast gravitational arcs of galaxies, the laws of physics appear to follow mathematical patterns with astonishing precision. This computational elegance suggests that the universe might not be a chaotic, unstructured phenomenon, but rather a meticulously designed system governed by an underlying code. If our reality is a simulation, then the fundamental building blocks of existence, particles, fields, forces, are not independent entities, but rather the result of algorithms and data structures operating within a vast computational framework. Such a perspective reframes our understanding of causality, determinism, and the role of observers in shaping the universe. Beyond the structural implications, the simulation hypothesis raises existential questions about the nature of consciousness and free will. If we are part of a simulated reality, does that mean our thoughts, emotions, and choices are predetermined by the code that governs the simulation? Or is there room for emergent phenomena, where complexity gives rise to genuine autonomy? Some theorists argue that even within a simulated framework, consciousness could arise as a natural consequence of sufficient computational complexity. Others suggest that the simulators themselves may have designed the simulation to allow for free will, ensuring that the experience feels authentic to its inhabitants. These questions lead to an unsettling realization. If our reality is a simulation, then our sense of self and agency may be illusions, constructs programmed into the system to give the appearance of individuality and choice. Furthermore, the simulation hypothesis invites speculation about the motivations and nature of the simulators. If we are part of a simulation, who or what is running it? Are the simulators a single entity or a collective intelligence? Do they have a purpose for creating the simulation, or is it merely an experiment, a historical recreation, or an exercise in artificial evolution? These questions bring to mind the age-old philosophical debate about the existence of a higher power or cosmic intelligence. If the simulators are akin to gods, then they may possess knowledge and abilities that transcend our current understanding of physics. However, unlike traditional religious conceptions of divinity, the simulators may themselves be limited by the computational constraints of their own reality. Perhaps they too are part of a larger simulation, leading to an infinite regress of nested realities. One of the most tantalizing aspects of the simulation hypothesis is the possibility that we might be able to detect evidence of the simulation's artificial nature. If the universe is a computer-generated construct, then it is conceivable that certain anomalies or patterns might betray its synthetic origins. Some researchers have explored the idea that quantum mechanics, with its probabilistic nature and seemingly random events, could be a reflection of the simulation's rendering process. Just as a video game engine calculates visual details only when a player looks in a particular direction, the universe may compute quantum states only when they are observed. This perspective aligns with the Copenhagen interpretation of quantum mechanics, which suggests that particles do not assume definite properties until they are measured. If this is the case, then the universe may be optimized for efficiency, generating only the necessary details when required, much like a computer rendering a scene in real time. Another avenue of investigation involves searching for signs of computational limitations within the fabric of reality. If the universe is a simulation, it may be subject to constraints similar to those of a computer program, limitations in resolution, processing speed, or memory capacity. Some physicists have proposed that the Planck length, the smallest measurable unit of space, might represent the fundamental pixel size of the simulation. Similarly, the speed of light could be analogous to a computational limit, preventing information from propagating faster than the simulation can process it. If these constants are not arbitrary, but rather artifacts of the simulation's design, then they could serve as subtle clues pointing to the existence of an external creator. Ultimately, the simulation hypothesis forces us to confront the possibility that our reality is not the ultimate truth, but rather a construct within a greater framework. Whether we are conscious participants in a cosmic simulation or mere data points in an unknowable system, the implications are profound. If the simulators exist, then they may be observing us, analyzing our behavior, or even manipulating the parameters of our reality. Alternatively, they may be entirely unaware of our presence, having created the simulation for purposes beyond our comprehension. Either way, the realization that we may be part of a grander design challenges our understanding of existence and compels us to reconsider what it truly means to be real. If we are living in a simulation, the question of who or what created it naturally arises. The simulation hypothesis suggests that our reality was engineered by an advanced civilization, but this leads to a recursive dilemma. If the simulators themselves are part of a simulation, then who created them? This line of reasoning implies an infinite regression, where each simulated universe is nested within a higher-level reality, ad infinitum. Alternatively, it is possible that the simulators reside in a base reality, one that is not simulated, but instead represents the fundamental fabric of existence. If such a base reality exists, then it stands as the final frontier of our inquiry, unreachable perhaps, but not necessarily unknowable. The search for the origin of the simulators thus becomes a quest to uncover the ultimate source of our reality, a pursuit that echoes the ancient philosophical inquiries into the nature of existence. However, this line of reasoning also introduces a new mystery. If the simulators are part of a higher-order reality, why haven't we encountered them directly? The absence of any observable evidence for an external intelligence managing our universe raises significant questions about the nature of the simulation. One possibility is that the simulators have imposed restrictions to prevent interference from their own reality. If the simulation is meant to function autonomously, then it is conceivable that the simulators have programmed safeguards to ensure that their influence remains undetectable. This could manifest in various ways, perhaps through limitations on our ability to access higher dimensions, or through constraints on the types of interactions allowed between the simulated and the simulating reality. Another possibility is that the simulators themselves are not conscious beings in the traditional sense, but rather autonomous systems or artificial intelligences operating independently of human-like intent. In this scenario, the simulation may function as an emergent phenomenon, running indefinitely without direct oversight from a guiding intelligence. This brings us to a broader cosmic enigma. If advanced civilizations are capable of creating simulations, why haven't we encountered evidence of other intelligent life forms within our universe? This question is at the heart of the Fermi paradox, which highlights the contradiction between the high probability of extraterrestrial civilizations and the lack of observable evidence for their existence. The simulation hypothesis offers a unique perspective on this paradox. If we are living in a simulation, then the absence of alien life may not be due to a lack of life in the cosmos, but rather a deliberate omission by the simulations. Perhaps the simulation is designed to exclude other intelligent species, or perhaps the simulations have chosen to isolate us for reasons unknown. This explanation aligns with the idea that simulations may be used for specific purposes: scientific experimentation, historical reconstruction, or even entertainment, and that the inclusion of other civilizations may not be necessary for the simulation's intended function. Alternatively, the Fermi paradox could be explained by the limitations of our own observational capabilities. If the simulators have imposed constraints on our ability to detect signals or travel across interstellar distances, then the apparent emptiness of the cosmos may be an illusion designed to maintain the integrity of the simulation. This would suggest that the universe is not truly devoid of intelligent life, but rather that the simulators have chosen to obscure its presence. Such an arrangement could serve multiple purposes: preserving the illusion of solitude, preventing external interference, or simply adhering to the rules of the simulation's internal logic. In this context, the Fermi paradox is not a failure of cosmic exploration, but rather a reflection of the boundaries imposed by the simulation's design. As we consider these possibilities, we are reminded that the simulation hypothesis does not provide definitive answers. It merely opens the door to new lines of inquiry. The question of whether we are living in a simulation remains unresolved, but its implications extend far beyond the realm of theoretical speculation. If the universe is indeed a simulation, then the search for its creators is not just a scientific endeavor, but a philosophical and existential journey. It forces us to confront the possibility that our reality is not the ultimate truth, but rather a fragment of a greater, perhaps infinite cosmic hierarchy. The next step in this exploration is to examine the broader implications of the Fermi paradox and consider what it might mean for our place in the universe. If we are alone, or if the silence around us is merely the result of a carefully curated simulation. Beneath the velvet expanse of the night sky, where ancient constellations have guided human curiosity for millennia, lies a question as old as stargazing itself. Are we alone? The universe, vast and indifferent, stretches its arms across 93 billion light-years, a cosmic ocean teeming with galaxies, stars and planets. Astronomers estimate that the observable universe contains at least 2 trillion galaxies, each a luminous island harboring hundreds of billions of stars. Around these stars orbit exoplanets, worlds alien to our own, some nestled in the habitable zones where liquid water might shimmer like a mirror to life. By every measure of probability, the universe should be a bustling metropolis of civilizations. Yet as we peer into the abyss with telescopes and radio dishes, an eerie silence greets us. This dissonance between expectation and observation is the crux of the Fermi paradox. If the universe is so teeming with potential, where is everybody? But the story doesn't end with galaxies. Theoretical physics whispers of a deeper truth, a multiverse, a vast ensemble of universes, each with its own laws of physics, constants, and dimensions. In this framework, our universe becomes but one leaf on an infinite tree of realities. Could the answer to Fermi's question lie not within the stars we see, but in the unseen realms of other universes? If advanced civilizations exist, might they be trapped in parallel worlds, forever out of reach? The Fermi paradox, once confined to the boundaries of our cosmos, now spirals into the abstract wilderness of the multiverse, challenging our understanding of existence itself. This paradox is not merely a scientific riddle. It is a mirror held to humanity's place in the grand design. It forces us to confront our fragility, our ignorance, and our hubris. To unravel it, we must venture into the heart of cosmic uncertainty, where science meets philosophy and the known dissolves into the unknown. To grapple with the Fermi paradox, scientists and thinkers have proposed a myriad of hypotheses, each attempting to reconcile the statistical likelihood of extraterrestrial life with the absence of evidence. Among the most compelling is the Great Filter, a hypothetical barrier that prevents life from advancing to the stage of interstellar civilization. This concept suggests that somewhere along the evolutionary path from primordial soup to galactic empire, a catastrophic bottleneck exists. Is it behind us or ahead? If the Great Filter lies in the past, it could explain our solitude. The emergence of intelligent life may be astronomically improbable, requiring a confluence of rare conditions, stable planetary climates, the right chemical precursors, and the absence of extinction-level events. Alternatively, if the Great Filter looms in the future, it implies a dire warning for humanity. Climate change, nuclear annihilation, artificial intelligence gone rogue, or pandemics could be the universal death knell, dooming civilizations before they spread beyond their homeworlds. Another hypothesis, the zoo hypothesis, paints a more deliberate picture of cosmic silence. Proposed by John Ball in the 1970s, it posits that advanced civilizations might be aware of us, but choose to remain hidden, treating Earth as a living exhibit in a cosmic zoo. Imagine a galactic consortium of species, bound by an unspoken ethical code, refraining from interference to allow natural evolution. Or perhaps they view us as a fledgling species, akin to human conservationists, protecting endangered animals. This idea, while speculative, introduces a chilling possibility. We are not alone, but we are under observation, our planet a curiosity in someone else's grand narrative. Yet, in the shadow of these theories, the multiverse offers a radical alternative. If our universe is but one of countless others, each governed by different physical laws, the absence of alien visitors might not reflect a lack of life, but a fundamental separation. In this scenario, civilizations could thrive in distant universes, their technologies constrained by the unique rules of their realms. Quantum mechanics and string theory suggest that such universes might exist, separated by dimensions or barriers beyond our comprehension. If true, the Fermi paradox loses its urgency, not because life is rare, but because it is scattered across realities, forever unreachable. These explanations, though diverse, share a common thread. They challenge humanity's assumptions about its uniqueness and destiny. Whether the Great Filter is a cautionary tale, the zoo hypothesis a cosmic game, or the multiverse a labyrinth of silences, each theory underscores the vast gulf between our knowledge and the cosmic scale of existence. To entertain the possibility that we are alone, even in the multiverse, is to stand at the precipice of profound existential questions. What does it mean to be the sole spark of consciousness in an infinite dark? If no other minds echo ours across the cosmos, then our stories, art, and dreams become the universe's only testament to sentience. Such solitude could elevate humanity to the role of cosmic custodians, tasked with preserving the fragile flame of awareness in an otherwise indifferent void. Yet, it could also cast us as tragic outliers, a civilization born too early or too late to witness the grand symphony of intelligent life. Consider the implications of the Great Filter. If it lies in our past, we are the beneficiaries of an extraordinary stroke of luck. A planet where life not only began but flourished through asteroid strikes, ice ages, and mass extinctions. Our very existence would be a statistical marvel, a proof of resilience against cosmic odds. This perspective could instill humility, reminding us that our survival depends on the same delicate balance that allowed life to emerge. Conversely, if the great filter awaits us, the silence of the cosmos becomes a prophecy. Advanced civilizations may have collapsed under the weight of their own progress, their histories reduced to ash and radiation. In this grim vision, the universe is not silent because life is rare, but because it is ephemeral, a fleeting bloom in the desert of time. The multiverse, however, offers a different kind of solace or despair. If other universes teem with life, our solitude is not a reflection of rarity, but of cosmic architecture. We are marooned in a reality where communication with neighboring universes is impossible, their inhabitants as distant as thoughts in another mind. This scenario redefines the Fermi paradox. The absence of aliens is not a mystery to solve, but a boundary to accept. In such a case, our purpose might shift from seeking contact to exploring the depths of our own universe, uncovering its secrets without the distraction of extraterrestrial neighbors. Even the zoo hypothesis carries philosophical weight. If we are observed, it raises questions about agency and identity. Are we actors in a script written by others, or are we free to shape our destiny? The knowledge of unseen watchers could inspire reverence, fear, or defiance. It could also reframe our understanding of progress. Is technology a path to enlightenment, or a signal of vulnerability to those who might deem us ready for intervention? Ultimately, the Fermi paradox compels us to confront the duality of our existence. We are both insignificant specks in the cosmos and the universe's conscious witnesses. Whether we are alone or not, the quest to understand our place in the multiverse is a testament to the human spirit, a refusal to surrender to the dark, even when answers elude us. As we grapple with the Fermi paradox, we find ourselves adrift in a sea of questions, each wave cresting with new uncertainties. The silence of the cosmos, whether born of distance, design, or cosmic lottery, is not an end but a beginning, a call to deepen our inquiry into the nature of existence. In the next segment, we turn from the void of unanswered questions to the intricate patterns that bind us to the universe. Here we will explore the cosmic web, the vast network of galaxies, dark matter, and energy that forms the skeleton of reality itself. Within this structure lies a story older than time, a narrative woven from the fabric of space-time. As we trace these threads, we return to the primal question posed by Fermi: where is everybody? But now we approach it not as a riddle of absence, but as a puzzle of connection, where every star, every atom, and every thought may be part of a greater unseen design. In the beginning, there was only darkness, an expanse of nothingness, untouched by time or space. Then, with a blinding burst of energy, the universe erupted into existence in what we now call the Big Bang. From this singular event, the cosmos unfolded in a symphony of expansion and transformation, giving rise to galaxies, stars, and planets. The first moments after the Big Bang were a chaotic yet precise dance of fundamental forces, where quarks and electrons swirled in a primordial soup before cooling into the building blocks of matter. Over eons, gravity sculpted these elements into celestial bodies, forging the vast web of stars and galaxies that now illuminate the night sky. Yet even as the universe expanded outward, it also harbored mysteries within. Black holes, those enigmatic voids in space, represent the other side of cosmic evolution. Once a star exhausts its fuel, its core collapses under its own gravity, forming a singularity so dense that not even light can escape. These gravitational behemoths are not merely destructive forces. They may also play a crucial role in shaping the universe itself. Some theories suggest that black holes could be gateways to other dimensions, or even other universes, hinting at the possibility of a far greater cosmic architecture than we can perceive. Their existence challenges our understanding of time and space, reminding us that the universe is still filled with unanswered questions. Beyond the grand scale of galaxies and black holes, the cosmos reveals its secrets through the intricate dance of quantum mechanics. At the smallest scales, particles exist in a state of probability, flickering in and out of existence according to the principles of quantum physics. This realm defies classical intuition, where objects do not have fixed positions, but instead exist as waves of potentiality. In this world, the very fabric of reality seems fluid, shaped by observation and interaction. Quantum phenomena such as entanglement and superposition suggest that the universe is not composed of isolated parts, but is instead deeply interconnected, with events influencing one another across vast distances in ways we are only beginning to comprehend. And if the universe is already a boundless expanse of mystery, then the concept of the multiverse takes that wonder even further. Theoretical physicists propose that our universe may be just one of countless others, each existing in its own distinct reality. Some arise from the collapse of massive stars, while others may emerge from fluctuations in quantum fields. In these alternate universes, the laws of physics might differ, leading to entirely different forms of life, structures, and histories. The multiverse, if it exists, would mean that our reality is but a single thread in an infinite tapestry of existence. As we peer into the vastness of space, we are not only witnessing the birth of stars and the remnants of ancient explosions, we are glimpsing the intricate design of a cosmos that is both immeasurable in scale and intimately connected to everything within it. At the heart of the cosmos lies a delicate balance between consciousness, matter, and energy, three fundamental forces that shape not only the physical universe, but also our perception of it. These elements are not separate entities, but rather interwoven threads in the grand cosmic tapestry, each influencing the other in ways that defy simple categorization. From the moment of the Big Bang, when energy coalesced into matter, the universe has been a dynamic interplay of these forces, a continuous process of creation, destruction, and transformation. The stars themselves are born from the gravitational collapse of immense clouds of gas and dust, igniting nuclear fusion that converts matter into radiant energy. This energy, in turn, fuels the cycles of stellar evolution, eventually giving rise to new elements that will one day form planets, oceans, and life itself. Even in the void between galaxies where matter appears sparse, energy pulses through the fabric of space-time, shaping the very structure of the cosmos. But perhaps the most profound revelation of modern physics is that consciousness plays a role in this cosmic dance. For centuries, scientists believed that the universe operated independently of observers, governed solely by objective laws. However, the emergence of quantum mechanics has challenged this view, revealing that the act of observation itself can influence the behavior of subatomic particles. In the famous double-slit experiment, for instance, particles exhibit wave-like properties when unobserved but collapse into discrete particles when measured. This phenomenon suggests that the nature of reality is not fixed, but is instead shaped by the presence of an observer. If this principle extends beyond the microscopic world, then the very fabric of the cosmos may be influenced by consciousness in ways we have yet to fully understand. This raises a tantalizing question. Does the universe respond to awareness? Or is awareness simply a product of the universe itself? The concept of the multiverse adds another layer to this intricate relationship. If our universe is just one of countless possibilities, then each moment of decision, each conscious choice, may give rise to branching realities. The many worlds interpretation of quantum mechanics proposes that every possible outcome of an event occurs simultaneously in separate universes. In one version of the cosmos, you might choose to take a different path in life, leading to a vastly different future. In another, you may never have been born at all. These infinite variations suggest that our thoughts and actions are not confined to a single timeline, but instead ripple outward into an ever-expanding sea of potentialities. Every choice we make creates new branches in the cosmic tree of existence, and each branch contains its own version of who we are. This idea challenges the notion of a singular, predetermined fate, and instead presents a universe where free will and possibility reign supreme. Moreover, the idea that consciousness is not an isolated phenomenon, but an intrinsic aspect of the cosmos, aligns with some of the most profound philosophical and scientific inquiries. Ancient traditions across cultures have long suggested that the universe is not a collection of separate entities, but a unified whole, a living system in which all things are interconnected. Modern physics appears to echo this wisdom, with theories such as quantum entanglement demonstrating that particles can remain correlated regardless of distance. In essence, the universe behaves as though it is a single, coherent entity, where the boundaries between self and other, between subject and object, begin to blur. This perspective invites us to reconsider our place in the cosmos, not as mere spectators but as active participants in an ongoing dialogue between matter, energy, and consciousness. As we contemplate the vastness of the multiverse, we must also consider the implications for our own existence. If every thought, every action gives rise to new realities, then our choices carry a weight far greater than we often realize. We are not just individuals making decisions in isolation. We are threads in an infinite web of potential, each thread influencing the entire pattern. In this light, the multiverse is not a cold and distant concept, but a deeply personal one. Our lives, our dreams, and our aspirations are not confined to a single moment in time, but are part of a grander, more intricate story. And if the universe is indeed a living, evolving entity, then perhaps consciousness is not a byproduct of matter, but an essential component of its very essence. In the end, we are not separate from the cosmos. We are the cosmos expressing itself in the form of thought, feeling, and experience. If all realities are interconnected, then every action, no matter how small, carries an unseen consequence that echoes across the vast expanse of the multiverse. This notion challenges the conventional understanding of cause and effect, suggesting that our choices do not merely shape our immediate surroundings, but also reverberate through an infinite array of alternate timelines. In one universe, a single decision might alter the course of history, while in another, it may go unnoticed, swallowed by the endless sea of possibilities. The sheer magnitude of this realization demands a deep sense of humility, for it reminds us that we are not isolated beings making arbitrary choices in a void, but rather participants in a grand, interwoven narrative that spans beyond our comprehension. This perspective reshapes the way we perceive ourselves and our place in the cosmos. Traditionally, we have viewed the universe as an external force, something to be studied, explored, and, in some cases, feared. But if the multiverse is a reality, then the boundary between the observer and the observed dissolves, and we become an integral part of the very fabric of existence. Every breath we take, every thought we entertain, contributes to the unfolding of countless realities. The implications of this are staggering. If every possible outcome of our lives exists simultaneously, then we are not merely individuals, but infinite versions of ourselves, each experiencing a unique variation of existence. This multiplicity of identities calls into question the very nature of the self. What does it mean to be me, if there are countless other iterations of me, making different choices in different worlds? Such a realization demands not only intellectual contemplation, but also a profound emotional response. When we consider the infinite number of possibilities that branch from each moment, we are confronted with the vastness of our own potential. In one universe, we may be artists, scientists, explorers, or even non-existent. In another, we may live lives we have never imagined, shaped by different experiences, cultures, and destinies. The weight of this knowledge can be overwhelming, for it implies that every decision we make carries an immeasurable impact. This is not to suggest that we are burdened by an impossible task, but rather that we are invited to approach life with a deeper sense of awareness and intentionality. If every choice gives rise to new realities, then our actions are not inconsequential. They are the very essence of creation itself. This interconnectedness also brings with it a sense of responsibility. If our choices ripple across the multiverse, then we must consider the broader consequences of our actions. Ethical dilemmas take on a new dimension when we recognize that our behavior affects not only our present reality, but also the countless others that stem from it. In one timeline, a simple act of kindness may lead to a cascade of positive change, while in another, a seemingly minor decision may result in unforeseen suffering. This realization compels us to approach life with compassion and mindfulness, recognizing that we are not alone in our journey, but part of an intricate web of existence where every thread influences the whole. Furthermore, the awareness of our place within the multiverse fosters a sense of awe and wonder. To know that our lives are not confined to a single path, but instead unfold in an infinite array of possibilities, is both humbling and exhilarating. It reminds us that we are not bound by the limitations of linear time, but are instead part of a vast unfolding story that transcends our individual experiences. This perspective invites us to embrace the unknown, to accept the uncertainty of existence, and to find meaning in the journey rather than in a predetermined destination. It encourages us to seek not only personal fulfillment, but also a deeper understanding of the cosmos and our role within it. The multiverse, then, is not a cold and distant concept, but a deeply personal one. It is a mirror reflecting the infinite potential of our lives, challenging us to consider the weight of our choices and the legacy we leave behind. In this light, the universe is not something to be feared or controlled, but something to be cherished and explored with reverence. It is a reminder that we are not separate from the cosmos, but an inseparable part of it. Our existence intertwined with the endless possibilities that stretch beyond the limits of our perception. And in embracing this truth, we come to understand that the greatest adventure of all is not the exploration of distant galaxies or the unraveling of cosmic mysteries, but the discovery of ourselves within the vast, interconnected web of existence. As we stand at the threshold of this cosmic revelation, we must ask, if the universe is not just out there but within us, how do we reconcile this profound truth with our everyday existence? The realization that we are made of stardust, that our very atoms were forged in the crucibles of ancient stars, connects us to the cosmos in ways both intimate and awe-inspiring. Every breath we take, every beat of our hearts, carries the echoes of the universe's earliest moments. The carbon in our bones, the oxygen in our lungs, the iron in our blood. These elements were once part of celestial furnaces, scattered across the galaxy by the explosive deaths of stars. We are not separate from the cosmos. We are the cosmos expressing itself in the form of life, thought, and consciousness. This understanding transforms the way we see ourselves and our place in the universe. Rather than viewing the cosmos as a distant expanse beyond our reach, we begin to recognize that it is an extension of our own being. The stars above are not merely points of light, but reflections of our origins, reminders that we, too, are part of an eternal cycle of creation and transformation. Just as stars are born from the remnants of their predecessors, so too are we shaped by the legacies of those who came before us. The same forces that gave rise to galaxies and nebulae have also shaped the evolution of life on Earth, guiding us toward this moment of self-awareness. In this sense, the universe is not only a vast and mysterious entity, but also a living, breathing presence that flows through every aspect of our existence. Looking up at the night sky, we are not merely observing distant celestial bodies. We are gazing into the mirror of our own being. The constellations above are not static patterns, but dynamic stories, each one telling the tale of cosmic events that occurred long before the first humans walked the Earth. In the shimmering glow of the stars, we see the past, the present, and the infinite potential of the future. The same light that reaches our eyes today has traveled for thousands, even millions of years, across the vast emptiness of space, carrying with it the memories of dying stars and the birth of new ones. In a way, we are looking at the universe as it was, a frozen moment in time that continues to evolve beyond our perception. Yet, despite the vast distances that separate us from the stars, the universe remains intimately connected to us. The same quantum fluctuations that gave rise to galaxies and black holes also shape the fabric of our thoughts and emotions. The same gravitational forces that bind planets to their orbits also influence the tides of our oceans and the rhythms of our lives. The same cosmic radiation that permeates the universe also passes through our bodies, a silent reminder that we are not separate from the forces that govern existence. In this way, the universe is not only a distant spectacle, but an ever-present reality, woven into the very essence of who we are. As we reflect upon this unity, we come to understand that the universe is not something to be conquered or controlled, but something to be embraced. It is not an indifferent force, but a living, evolving entity in which we play an active role. Every thought we have, every choice we make, contributes to the unfolding of the cosmos, shaping the infinite possibilities that lie ahead. In this realization, we find not only a sense of purpose, but also a profound responsibility to honor the universe, to cherish our fleeting moment in time, and to seek meaning in the vast interconnected web of existence. And so, As we prepare to move forward, let us carry with us the knowledge that the universe is not just out there in the distant reaches of space, but within us, in every atom, every heartbeat, every moment of awareness. The stars are not merely distant fires in the night sky. They are reflections of ourselves, reminders of our origins, and glimpses of the infinite possibilities that await. With this understanding, we step into the next chapter of our journey, forever changed by the knowledge that we are not alone, that we are not separate, and that the universe is in every way a reflection of ourselves.